students, but rather it should be used to give feedback to students on how well they're doing, if there are areas that they need to improve on. Because we assign so much Okay. What I've done is we looked at the syllabus of QT01 and QT02 and the coverage of what we've done last week and half of this week, what we'll be doing today and tomorrow. And I've extracted out about 12 different overall topics. If you look at the introduction, you'll see the instructions of basically repeating what I've said. Oh my God. Hang on just a second. So, uh, you'll see the instructions just for reference. Like I said, we've divided it into 12 subsections. The idea is to have a dialogue with the LLM, right? That's all that it is. And at a minimum, you've got to do at least 5, it'll ask you a question, you answer it, there'll be a follow-on question. You can ask it a question as well, but that dialogue goes on for a little bit. If you enjoy it so much that you want to, get even more information, you can just say /continue. So you can keep going. Once you're done, you can say /quit to complete the session. and slash reset, if you're not happy with what you've answered and you're uncomfortable with it, if you say reset, it will reset that particular conversation. So if you've had conversations on the other 12 topics, that's perfectly fine. That doesn't go off. So it just resets this conversation. So that's kind of the options that you have in the chat itself. Why is it called Surya? Chandrani Surya. So this is where it is going to put light over our knowledge. So we are going to, we're going to find out what's hidden in the shadows of our minds or of our ignorance. Okay. So out of these 12 topics, the ask is, and especially with QT01 and 02, there's actually quite a lot of oh no, hang on, I'll eventually get the hang of this. There we go. Okay. So so these are kind of the topics that you have, right? Quantum states and Hilbert spaces, observables, angular momentum, density operators. Choose the ones that you enjoy. Do at least 5 of them. So it's not expected that you do all of them. We are all from different backgrounds, physics, chemistry, computer science, electronics. You've connected well with some topics, maybe not so well with others. So don't feel stressed out. You don't have to do all of them, but do at least 5, and do go ahead and have the conversation. As an example, I think I lost it, or yeah, I think I lost it. Let's see. Oh no, I lost it. Okay. So I had like a whole conversation laid out so I could walk you through it. But let's say, how would you explain the physical intuition behind superposition to an undergrad engineering student who's familiar with classical systems? Try to give as descriptive answers as you can. And what I wanted to show you was the feedback that you get at the end of it, but in the interest of time, I won't do that right now. Do go ahead and work through the conversation. At the end, after 5 turns, you will get, hopefully, and if you don't, please let me know, you will get a summary of what the LLM feels you have understood well, and more important than that is what areas you should focus on, right? So depending, and it's perfectly fine to say, hey, I don't know this. That's perfectly okay as well, because you're not being scored on it. The goal is to identify what areas we need to focus on, right? So the end goal, the target is very different from just getting a numerical score at the end of it. All right?
This should also be told to Reddy, sir.
Yeah, no, absolutely. We've told him this. We started out with the challenges that we see in the system that we have right now.
Normally, officers are used to have a numerical feedback.
Yeah, well, see, and it makes a lot of sense depending, because that is what they're trying. Like even when we look at admission to colleges, right, we need some way of comparing students, and it becomes very convenient if we have a quantitative score out there, right? So for that purpose, it makes sense, but then the underlying principle of, the whole point of education is to help people learn. That gets completely missed out, right? No, so when we presented this to him, we started out with what we saw as the big problems of the current, which was probably not a very smart thing to do, but yeah. Kunj.
Related reason to do this is also getting students job ready, and job requirement is often to do things on your own, learn things on your own, and this kind of a system engages them in that mode. And when you're doing a job in a company, you rarely get numeric score, but you do get feedback.
But here I want to give my feedback.
Yes.
So I was talking to Ahmedabad University faculty member.
Mm-hmm.
They are friends with their private university. what happened, they have got very good faculty all from abroad and all, but they are good faculty. They have selected, they pay. So they adopted a procedure that student come, whoever is qualified student comes, talks to the faculty member, and no nothing, no exam and all those things. If they feel after conversation, they can
Right.
recommend he or she is the solution.
Right.
So what's happening? Guys who are from good English schools and all these private universities, they are smart in talking and all.
Yes, they speak
and
well.
impressed, but
Yeah.
they speak well, very confident and all
Yeah.
those things. And they don't know basics even, mathematics, simple
Yes,
mathematics.
yes.
They don't know
Yes.
physics. So they get admission.
Yes.
Because they can talk nicely. and
Yes,
all,
absolutely, absolutely.
and they are getting admission. So most of the faculty, the staff, they decided. So
Yeah.
faculty who teach, they are saying they don't know anything. and
How did
they
you
are
get
selected.
admission? Yeah, yeah.
So I feel there should be some mix. It's not just like
Agreed.
and you are confident, you are talking,
Yeah.
you can write nicely, you know very well English, you can write something very nicely.
Right.
So there should be some mix, balance should be there.
Yeah. So, so in fact,
Exam, you know some basic,
yeah.
not completely on that, and then
Yeah. So two comments based on what you said. Agree completely. We do need to add a component of, maybe a little bit of problem solving, testing actual facts, because even that is important. We can't ignore that completely. And the previous version, so the other FDP that we had a quiz module where, so out here this is, multiple choice kind of thing. But we had another Chandra module, which was, it would give you a very specific numeric problem to solve, right? So you actually had to solve it and put in the answer and verify that it was right. So yes, but I agree with you, that should be part of it. But the other thing I wanted to say is, when we have humans evaluating another human system, environment, whatever, there is bound to be some amount of subjectivity, right? There's this very famous study that some behavioral economists did, where they found that when there's a case being heard in front of a judge, right? If the sentence is being pronounced after lunch versus before lunch, right? So after lunch, they are more likely to get a lenient sentence. Because paid bhar gaya, he is happy, he is satisfied. So that does come in, right? But to me, that is actually an argument in favor of this. Because an LLM doesn't get tired, it doesn't get fatigued, it's not hungry, it doesn't feel like going to sleep, right? It's relatively standardized. And it is, so I have a few interns at my company right now, and I literally told one of them that, so I encourage all of my interns to use LLMs to the full, right? And I go over the conversation with them, and I was telling them that the prompts that they were putting were so unhinged, even I couldn't understand what they were trying to say, right? I mean, this student was trying to figure out what the Hessian of a system of equations is and how that impacts convergence and all of that. And I couldn't understand what the question was, but the LLM did. The LLM did, which was brilliant. I mean, it was able to figure that out. So to some extent, and I haven't tested this out, but I'm pretty sure we can have this, do the same conversation in Hindi or Marathi as well, or Gujarati, and still perform just as well. Right? So I think this, what you said is actually something that is in support of what we have right now. Yeah. But thank you for the feedback. That's and please, guys, this is something that we are very passionate about. We've built this. It's for people who are used to working with LLMs, it's more of an IT project. But there's a lot more in terms. So the technology isn't the important thing. The design and how we use it is what is important. So one is, as end users or as guinea pigs, we will be using this to evaluate the course itself, right? So depending on how well you have understood the topic, it tells us how well we taught that topic, right? That's one part. But the other part is we want to test it to see if we can scale it up, right? This is not just for this course. but we are interested in taking this to not just for our use, but for universities around India, and have them use it as an evaluation tool as well. Right? So from that perspective, your feedback is really, really important. So not just the feedback that you're getting from Surya, but also tell us what worked, what didn't work. Of course, if there are any problems, if it doesn't render some math correctly, or if it makes a blatant mistake, definitely tell us. But also, what did you think? Does it make sense? Would you like to use this in your classrooms as well? Right? Not just for quantum technologies, but whatever subjects you're teaching. And if you are, please, we are more than happy to support you out here. Okay. Let me just take this to also talk about the funding that we've gotten from, or that we hope to get from the government of Maharashtra, also includes a budget for continued use of Quantex LMS and this evaluation system. So our hope is that you go back to your colleges, you use the system, we will customize it for the course that you are conducting. We are going to be doing a lot more video recordings that will be part of the system. And for this particular for this particular LLM, we have a budget for each college, right? So it's not going to cost you anything, and it's a pretty good budget. So even if you have multiple classes, 60 students using the LLM, go for it, right? It's there. There's no overhead for you guys. Just leverage it as much as you can.
So for example, for the next semester, we will have 40-50 students.
Yes.
So how will they?
So we'll discuss how we can do that. But basically, we'll enable the LMS the way you guys were enabled.
They have to send their email IDs.
Their email IDs. We'll enable that, and then everything else. But more than that, it's not just this LMS. We want to work with you to customize the content of each course for what you are doing. That's one. And how you want to do the evaluation. So for example, we didn't get a chance to try it out, but what
For example, we teach for 2 weeks.
Yeah.
And then take a test.
Yeah.
Just to understand whatever.
Yes.
They have understood.
Yeah.
So this might be.
Absolutely.
One thing.
Yeah.
2 units, 1 unit test, 1 unit test.
Test, yes. And this can be offline, right? I mean, it doesn't have to be in class or something like that.
Okay.
Yeah.
And all the scores we will get.
Yes. And then we can, so right now I'm not tracking, so I'm only tracking at a high level, what is the understanding of students. So if I take module 1, like this is, I don't know, entanglement and superposition, right? So what was the overall understanding for this particular module?
And we need internet for that, or they can.
Yeah, internet is required.
No, we cannot take. Like,
It's not offline, yeah.
Happening.
Well, I mean, I can convert this to an app, that's not an issue, yeah.
I think internet will be needed.
Internet is needed, yeah. No, but also, like if you have something particular that you want to test as an instructor, if you want to say that, I want to really focus on if they've understood in all of the formulae, or you could say, okay, formula I will give, but can they interpret it? Or you can go one level deeper and say, okay, can we go ahead and not just interpret it, but also apply it in certain scenarios? So we can talk about that and construct that particular. In fact, later on, maybe I'll show you the thought that's gone into this in terms of, when you ask a question, you could just ask, like I just said, what is a fact of this particular scenario? Or you could say that, hey, here's a new scenario that you've not seen before. How are you going to think about solving this particular problem? And that requires the student to really think about what they have studied and understand how to adapt that to a different thing. Or we present a scenario that is, and a solution that is slightly wrong. And we say, can you identify what the problem is out here, right? So there's a number of different strategies that we've implemented in the conversation that you'll see, right?
Can it generate problems also?
It can. This one is more about a conversation, but if I show you the other FDP that we had in June, it was generating problems. So for each topic, based on what was covered, it would generate that particular, something related to that topic. And in that, so the way we had, like the continue, reset and done approach, out there, you could actually set the amount of, maybe I'll pull it up later on and show it to you, but you could set the amount of mathematical depth you wanted, both for questioning as well as giving explanations. Then how much interaction, so out here this asks you, like if you ask it a question, it will try to get you to figure it out. It will give you one level of answer and it will say, now what do you think about this? How would you think about this? So you can adjust that to, say that, okay, just give me the answer, reduce this thing. And the third was you could define how much you wanted it to focus on intuition and understanding versus, just saying, okay, this is a mathematical derivation of something, for example, right? So all of this is customizable, right? Based on your personal teaching style, what your goals are in the course, what you want from your students, this is something that we can tailor to your use, and we'd really like you to start leveraging this. And like I said, we will work with you on customizing it for your purposes. And there is a cost associated with it, but for the first, I think 2 years, definitely for this year, this semester and next semester, it's not going to be translated to a bill that comes to your department or anything like that. Right? Yes?
Firstly, I tried it yesterday a bit, but how do I see the history that I'm not sure?
So, history for Surya or for?
Chandra.
So, right now I've not saved it, but I can enable that.
Yeah, because
Yeah.
I might have asked some question
Yes,
to start with,
yes.
for understanding myself.
Yeah, yeah.
Then I want to.
If you go back again, it's lost. Yes, yeah.
So,
I can enable that.
Yeah.
Yeah.
That is one. Number two, I figured out that it's in distraction mode. What I mean to say is that I asked some question.
Yeah,
It tried to give me an answer, partially, not
Yeah,
very
yeah,
correctly.
yeah.
And then it put something which I didn't ask. And then in the end it said you want to go on that track.
Do you want to go there? Yeah,
So,
yeah.
so I had to bring it back.
Yeah.
I said like I didn't want to, I didn't ask you that question.
Yeah, yeah, yeah,
This one.
yeah, yeah.
And then it came back on the track.
Yeah.
That is happening pretty often.
Okay, I'll look at that. If something like that happens,
So if you can enable the history, I can show you what
yes,
is happening.
yes, yes. But in the meantime, if you can just save it if that happens again and send it to me, I'd really appreciate it.
But can I see
Yeah.
yesterday's communication with Chandra? Is it possible?
No, so this doesn't save anything.
Okay.
And that was an intentional choice because people might feel uncomfortable.
But I think that configuration should be given to the user. And
Yeah, so it can be. The thing is, so I'm using a SQLite database at the back end, right, where I'm logging how many times it's been used for which module, right, but I'm not logging the content of the chat,
Yeah.
right. The problem is if we want to make the content persistent, right, I'm worried that the user might feel uncomfortable about that.
Okay, so
So
let me give another option. Why can't I export my current chat? To a
I can do that. That's easy to do.
It's not
Yes.
history, but I have the
Yes.
history of it.
Yeah. So it should be saved at your end,
Yes.
not at the back end.
पब्लिक
Yeah.
बेइज्जती नहीं होनी चाहिए.
Yeah. No, I can work on that. That's a good point.
Export is, I think, the easiest.
Yes,
Then
yes.
I decide whether I need to export it or not.
Yeah. Yeah. Yes. Great. Any other questions, comments?
How to verify the correctness of whatever?
That is a problem. It's an LLM, right? So it is possible that it is going to hallucinate some stuff, right? That is definitely a problem. But I think for the level at which we are targeting it, it should be safe, right?
It's
Yeah.
really a great problem, this LLM. Subject which you know very well, you know that there is problem, what is it's writing. But subject you don't know very well, you think
You just
that
accept
is
it.
coming from.
So there's this really nice article by a guy who said that, I used to follow some opinion writer and I used to think he knows a lot what he's talking about. But then he wrote about a subject that I'm working in, right? And I realized he doesn't know anything. So then why should I trust him when he talks about something else? Yeah. But here's the other thing, right? So out here, it is grounded. It has been instructed to strictly follow the content of what we are giving it, right? So that reduces the chances. It doesn't eliminate it, but it reduces the chances of hallucination. Kunj, were you?
Is there a way for one of these interfaces also to send in a question to say Professor Zog or to Professor Kanere
Or
or within
citation,
the community of users?
or might be citation that go to equation 1 of this book.
That we can do. So the citation is easy to do. The sending a question, so what we are doing, like I said, is we are aggregating all the responses to identify which modules have been understood by students and where they need to work on. So that aggregate stuff we'll be sharing with the instructor. But this is actually a good point. Like if so is this something? Yeah.
The implementation will be something like this: you give a separate tag
Yeah.
for question,
Right.
and then those are aggregated on your end,
Yeah.
and you further kind of segregate them as per the area.
Right.
Then if the area falls under Dr. Zom's expertise, then you give it to him.
Yeah.
And like this.
Right. So explicitly the student saying this is a question that I.
It's like some kind of small tag, like
Yeah. Yeah.
the HTML tag or some symbol you can decide.
Yeah.
I'm making notes, Sriram.
Oh, okay. Yeah. Because I realized once it goes above 2 or 3, my cache starts filling up. So okay. Yes. So thank you. That's a very good point. Yeah. This we can add citations.
Citation book,
Yeah.
we can check from.
Or further references. Yeah. Anything else?
But to the point, if possible, for example, this theorem is taken from somewhere or.
Yeah. Yeah. Yeah.
Perhaps one more suggestion, I am just thinking aloud. Just like we put a separate tag for question something. Let's say that in the list of instructors, I know who the instructors are, and I have the facility of
You can
I can
at
call
that particular.
that particular person.
Yeah,
then
yeah.
The
So-
trigger goes to him.
Yeah. So I don't know that we've done it for this installation, but I have another instance of the LMS where we've enabled discussion forums. So people can put in their questions, other students and even instructors can reply to those.
But can
So
I refer to an instructor?
yeah, yeah. So no, but I'm just trying to think whether what is the boundary between LLM based interaction and a discussion forum, because I can very well imagine that. So right now, if a lot of people are asking the same kind of question, right? Then even if they don't tag an instructor, it is something that is of interest to many people.
So essentially news group that we had a long time.
Yeah, yeah. So that's what I'm trying to think in my head. Like, how do we draw the line between the two of them, or maybe we integrate all of those functionalities, right? Yeah.
But
Okay.
in general, you will not get reply from the instructor. 3 questions or not you will get, unless until instructor is paid handsomely for answering those queries. You will not get after 1 or 2 queries.
Voluntary things.
So. So we're drifting a little bit off topic, but I'm a big fan of
Open source.
No, not open source. Well, open source is good, but if somebody is delivering something of value, they should be properly remunerated. They should be compensated for it, right? And I don't know. I mean, I've come across some yahoos who think that do things for the betterment of society, but I actually feel that if you compensate people well, they will do more for the betterment of society than just relying on their good instincts. I mean, everybody needs to, everybody aspires to a good standard of living, so there's nothing wrong in that. So, yeah.
This particular point we discussed in some different sense. We said that after this is over, he should not be detached,
Yeah,
and we should have a continuous interaction through something of what you are saying, at least till the period what is appropriate that you think, maybe a semester,
yeah.
till the course actually is over. So in that sense, we would be in touch if that arrangement is made, and be in touch means not just for hello,
Like a scheduled,
kind
yeah,
of discussion,
yeah.
technical discussion, scientific discussion.
So,
It can be arranged probably.
Yeah.
With the designated inspector, since we
Yeah.
are involved with designated.
And then maybe before we end, maybe on Thursday, tomorrow evening, let's plan at least the first 3 9 months of that kind of
Yeah.
periodic thing.
So some
before we go on.
arrangement,
Yeah.
it's either whatever forum discussion
Yes.
groups or through this whatever.
So I just wanted to mention, so Professor Kanare had said this right from the first conversation that we had about this course itself, that it shouldn't just be a 2-week thing. And they had volunteered that, you know, we'll be available, you can set up like a weekly call and, you know, we can discuss with faculty members. If you're planning on talking about a subject next week and you want to discuss it with us, we're going to be available. So he had volunteered this, like, so it's not, you know, just as a follow-on to what we're talking about, but this is something that he's been passionate about right from the beginning, right? So, so yeah, let's talk about that as well with everyone, so we can schedule that too, right? Okay, anything else? Okay.
So
Uh,
does this, you said try 5 turns.
Yeah.
Does it stop after 5?
Yeah, so after 5 turns, it will give you a feedback on the conversation that you had. If you want to continue, you can just say /continue and you can continue the conversation. To end that, you say /done. But the feedback gets triggered. So essentially what we have is, there is one LLM that you see out here, right? And that is, it's asking you a question, it's looking at your answer, it's asking you a follow-on question, it's giving you hints and so on. So that is one thread of execution. Parallel to that, there's another LLM that is monitoring the conversation and figuring out how much you have, what is the level of your learning or understanding or knowledge or all the parameters that we talked about. So it's actually 2 threads running, one of them is hidden. But my point was that evaluation gets triggered only after either 5 turns or if you say /done. Right? If you don't do that, if you just do 1 or 2 questions, you know, it's just okay. It doesn't trigger anything. Right? Okay. Anything else? So another example of how this technology can be used to scale is what Varsha, right? Harsha madam has developed. And I am absolutely flabbergasted that it hasn't been put into widespread use already. So you have a question paper, you have an answer metric for every question, and she's developed an LLM that can automate that whole evaluation process. So just imagine, you know, you have board exams or you have a class of 60 people and you've got to sit and score all of them. Instead of that, scan it, convert it to text, all of this is automated. Well, maybe not the scanning, but.
Without human intervention, the papers are evaluated by LLM.
Yes, and it turns out that from the metric that they had put up, the LLM is much more consistent than a human evaluator.
It's fair. More
So it's more fair, yeah. So,
Kind of softwares are already there, they are being used.
but it's not being used, that's my, that's what I find really frustrating. I mean, it should be, right?
In India it's not popular, but in US and all they're using it.
They are using it, yeah.
I talked to the president using it.
Yeah. And I would argue that we need it more out here than out there. I mean, the
And
volume
what
of
they do, first 5, 6 they will evaluate.
manually and use that as
They
the,
use that, they,
yeah.
They take it, then on
Right.
basis of that rest of the
Yeah.
150 they will evaluate.
yeah. You don't even need those first 4 or 5. Like normally what I've seen is when you create a question paper, you have a model solution and you assign marks for each step, right? So once you have that metric,
But then it has to be typed on the computer. It cannot be handwritten.
no. So that's the thing. She took
Handwritten also.
handwritten, scanned them,
Okay.
That's what they do.
you do OCR, yeah, text extraction and yeah.
Then it should.
Yeah. Okay. So with that, once again, please do this by tomorrow because Friday is our convocation, and talk to us about how you can leverage this for the courses that you're doing this semester and next semester as well. All right. Yes.
Just to add up to the discussion,
Yeah.
the last one, I have something against that, what is being done, unless rather it is being used for specific purpose, where you know that the way I arrive at the answer perhaps is
True,
very
true.
unique,
Yeah.
and that 2 steps are well defined.
Yeah.
Otherwise you kill creativity in this.
Sure.
And then some students who tend to think differently stop doing that.
Absolutely. But I would argue that if you look at, board exams, right?
That is a problem, because if you see in the older days, 1980s, in essay I would never get, let's say, 12 out of 15.
Yeah.
I will get 10 or 11
Yeah,
out
yeah,
of
yeah,
15.
yeah.
Today they give 15 out of 15 because they
So-
have understand these things.
Right. So obviously there are some kinds of questions that are amenable to them. So an essay question is like a subjective thing.
Yeah, but
right?
even in science, some questions may be lead to creative answers.
Right. No, my point is that in science, if I were writing, let's say, engineering exam or even 12th standard science, right? If I come up with a very creative solution, the examiner who's, looking at each question or each answer book in 5 minutes or less, right, is not going to care to look at it and evaluate it and say, oh, this is brilliant.
No, not exactly. So
Right.
essentially, very few examiners who might do that,
Yeah.
we are excluding them with this argument. Kind of. We are
But we are also excluding the 95% who do not do this.
that's okay, na. But
It's
no, it's more important that some people are actually doing it.
if they were to apply to all of the answers,
So in
yes.
board exams, actually what happens is there is something called moderation also.
Yeah.
So at that level, some of these things should be taken care of.
Yeah, if the examiner raises it up to the next level,
Not exactly. I will say, I know my uncle was a moderator,
mhm,
and that's a Marathi paper, and the boy used the word Bhaskar for Surya.
yeah.
Okay, and the examiner didn't know that.
So yeah,
But when it went to moderation, then he
so my point is that went to the moderator.
yeah.
What about the 95 that didn't go to the moderator?
But if my uncle would have been the examiner, he would have not.
Again, so how many of the examiners are actually,
No. So the
Yeah.
incompetency of majority of the people cannot be an argument to implement this.
no, I think it is an argument to implement this because we are addressing the main issue that we've seen, right? One issue is the incompetency of the examiner. And when it comes to creativity, I would argue that an LLM is not in this particular case, or yeah, do you want to add to that? Yeah.
ऍक्च्युली सर जसं म्हणाले मी थोडं मराठीमध्ये बोलते सर. तुम्ही जसं म्हणालात की भास्करला सूर्य हा शब्द त्यांनी वापरला आणि जर इव्हॅल्युएटर माहित नसेल तर पण एलएलएमच्या केसमध्ये जे एम्बेडिंग्स असतात ते कॉन्टेक्स्चुअल एम्बेडिंग्स असतात. सो द एम्बेडिंग्स ऑफ भास्कर अँड द एम्बेडिंग्स ऑफ
हे फक्त एक
सूर्य
उदाहरण
Right.
दिलं, म्हणजे आय अंडरस्टँड की तिथे कदाचित ते सोपं आहे, पण तुम्ही सायन्स मधला किंवा गणितामधला एखादा प्रश्न बघा.
तिथं कॉन्टेक्स्चुअल
So-
टेक्स्ट आहे त्याचं कॉन्टेक्स्चुअल रिप्रेझेंटेशन
Would be the same. Yeah. No, so hang on one sec. So two things. So one is what you are saying, absolutely. An LLM would not make that mistake, that they don't know what Bhaskar is, right? But more importantly, hang on. More importantly, the machine does what we tell it to do. So if we tell it that this is the model answer and you have to strictly follow it, it will do that. If we say that, oh, by the way, if you come across an answer that makes a lot of sense that doesn't fit it out here, evaluate it and escalate it.
There is an assumption of quote unquote making sense. I will say,
Right.
let's say I teach a subject called data structures in
Yeah,
data science.
yeah.
Now many times in last 10 years or 12 years, I have learned many things from my own
From students, yes.
Because if there was a question which I thought is difficult and I had two solutions in my mind.
Yeah. They've come up with something completely ingenious.
I
Yes.
have got at least 3 more solutions for the same
Yes,
problem,
yes,
which
yes.
I had not thought of.
Yes.
Now I have made a list of all those solutions.
Right.
It's my database.
Right.
And I say that these 5 solutions at least I know.
Right.
Now what I do is, now because of the load balancing and everything, many times the lab gets done by my PhD
Yeah,
student.
yeah, yeah.
Now what I do is these 5 solutions, of course I give it to him.
Right.
saying that-
Right.
But then there could be a possibility of 6 solutions.
Yes. And I would argue that an LLM would be able to look at a completely new solution and evaluate it better than a PhD student with a stack of 5
But
solutions.
then we know training is based on the existing information.
So if we are talking about evaluating a PhD thesis, an LLM may not be adequate. But if we are talking about evaluating undergrad question papers, I would argue that LLMs are smart enough to do that.
With the risk of being politically incorrect, I will say it's the exactly opposite.
Can I just tell
That's
you,
fine.
This is a very interesting topic. Actually, it needs a very different level of discussion.
True.
So, this is the correct forum to.
True, no, thank you.
We should focus on something which.
Thank you.
for which we are assembled.
Yeah. Let's.
I have nothing else to say.
No, please.
But let's focus on what we are supposed to do.
Yes. No, thank you very much.
It's a debatable point, and I can raise 10 such points.
No, that's absolutely valid, and thank you. Let's save the discussion for later.
So many questions, I just,
No, I think it's great.
I just wanted to make sure that it doesn't go through as it is.
Yeah.
So maybe I will answer all your questions after this discussion.
I have doubts, madam.
Yes,
Yeah,
yes,
we
sure,
will
sir.
discuss that.
But we can talk. I think the important thing is we can have a conversation about it. I think that's the important thing, right? Okay, let's get on to the subject of this session, which is computational complexity. I am going to talk about a few broad areas and try to bring that together. And you guys can tell me how successful or unsuccessful I am. So what I'm going to talk about is start with something that we said a couple of days back, which had to do with Turing machines and why Turing machines as a model are important. Because they allow us a precise way of specifying what the running time of an algorithm is, which is basically the number of steps that our head takes over the tape. It also gives us a sense of how much space a particular algorithm is going to take, which is the number of cells that are used in the execution of the algorithm. And a couple of examples that we saw last time. If you have a problem like SAT, or satisfiability, running time for SAT is, if I have n inputs, n Boolean variables, the running time is, anyone remember? It's exponential, right? It's 2 raised to n because we have 2 choices for every variable, and the only known algorithm is an exhaustive search, right? There are lots of heuristics that work very well, but effectively it's an exponential algorithm. And an algorithm, an example of an algorithm that works in polynomial space but exponential time is something like a board game, because the space, actually even SAT, does SAT require polynomial space or exponential space? Polynomial space, because you just need enough space for those variables. You plug in their values and you're evaluating it. Once you evaluate one set of values, you can just go to the second one. Okay, so that's kind of what we covered last time. What we didn't talk about too much is how we classify these problems, right? So I just kind of vaguely said, yeah, this is exponential, this is space, this is polynomial. But what I want to talk about is something called the NP complete class of problems, right? And effectively, like if you remember, the class P is problems that run in polynomial time on a deterministic Turing machine. The other class N, what does NP stand for? Non-deterministic polynomial, not non-polynomial time, non-deterministic polynomial time. So couple of definitions. So one is that if a problem, if a solution can be verified in polynomial time on a deterministic Turing machine, then that problem is said to be in NP. So that's a class of problems that can be verified in polynomial time, right? It turns out, and we're not going to go through all the derivation of this, but it turns out there's a class of problems that are called NP hard, right? And they have a very, very interesting property. So what happens is we can transform one problem in NP hard to another problem in NP hard in polynomial time, right? So from a running time perspective, these problems are equivalent, right? And you'll be surprised at the kinds of transformations we can do. There are some beautiful constructions. So for example, 3-SAT is satisfiability, it's a Boolean formula. But you can actually see how you can convert a graph problem with nodes and edges into a Boolean satisfiability instant in polynomial time, right? And therefore, now here's the kicker. These problems that we are talking about, like SAT for example, we don't have a polynomial time solution. We don't know if there is a polynomial time solution. We suspect there is, but we don't know, right? But if we were to get a polynomial time solution for one problem that is NP hard, then by definition, we would have a polynomial time solution for all problems that are NP hard.
Shall I add something?
Yes.
The qualifier could be when the solution itself either is verifiable in polynomial time or
Yeah.
not. So the kind of problems, perhaps the NP complete that we are
Yeah.
going to, are the ones where the solution is verifiable in polynomial time.
Yeah.
If the solution is not at all verifiable in polynomial time,
It's-
it's not in NP.
It's not in NP, yeah. So that's what we started out with. So first is NP is you can verify it in polynomial time.
So can you please repeat this?
Yeah, I'll actually write it down. Hang on. Okay, so this is the class of problems that can be solved in polynomial time, right? What are the kinds of problems we're talking about? Sorting a list of numbers, right? Graph traversals, they're all polynomial time. Okay, I'll get to those examples a bit later. But you know, even problems that seem to take a lot of time, like matrix multiplication is order n cubed, right? So these are all problems that are problems in this class P, right? NP is the class of problems whose solutions you can verify in polynomial time on a deterministic Turing machine. So of course, 3-SAT, what else were we saying? Finding the k clique in a graph, or finding an independent set in a graph. All of these, if you give me a graph and you say that here is a clique of size k, I can verify if that is indeed a clique or not, right? So I can verify the solution in polynomial time. Why is P in NP? Because if I can solve the problem in polynomial time, I can also verify the solution in polynomial time, right? Okay, and what Sir was saying is, so when I start talking about NP hard problems, right? So first of all, there are problems outside NP which we can't even verify in polynomial time. I'm going to give you a very interesting example of this later on, right? But so there's this class of problems, but there is also a class of problems that we call NP hard. Okay, and these were the problems that I was saying you can transform one into the other in polynomial time, right? Very interesting constructions. We are not going to go into that because it's not relevant to quantum computing, but it's like a whole field in itself, right? These problems that I can both verify in polynomial time as well as problems that belong to NP hard, right? These are a very famous set of problems that are called NP complete problems, right? And so there's this history. So back in the 20th century, there was this International Congress of Mathematicians or something. David Hilbert, a German mathematician, proposed a list of, I think, 18 problems.
Hilbert space
Techasnavania. So he sorry? 25, okay, sorry, 25 problems, which he said so basically he set the course for research in mathematics for the next century, right? And one of those problems was, I can't say the German word, but it was something called the halting, was it the undecidability problem. And Turing's Turing machine formulation was a solution to one of those problems, right? But anyway, so in this century, people were like, you know, what is the equivalent of Hilbert's problem?
Incompleteness problem.
No, Gödel was incompleteness. That was this guy, right?
Gödel proved that in any theory,
You can either axioms, yeah,
based on axioms, you can find a statement which is neither provable nor
nor unprovable. Turing proposed a Turing machine as a model for that particular problem. Yeah. So he didn't solve the problem. You're right. He provided the platform for it. But this century, there was like, okay, you know, what's the equivalent? And in the US, there's this guy called Clay who had a lot of money. He set up this thing called the Clay Mathematical Institute, and they proposed a list of, I think, six millennium problems. And you can look at it. It's an interesting list. But one of them was is P equal to NP, right? And if you solve this either way, either prove that they're equal or that they're not, I mean, you'll get the $1 million prize from the Clay Mathematical Institute, but you'll get a lot more than that, because this is like, anyway, most people believe that it's not, but who knows, right? Opinion varies as time goes by. So we don't know whether, just because 3SAT takes an exponential amount of time, we don't know that it cannot be solved in polynomial time. So far, for the last 55 years, nobody's been able to come up with a solution. But when you were talking about somebody might come up with an innovative solution, so there is this approach in linear programming that was developed by Danzig, right? And the story goes that it's there in his obituary. The story goes that he was a student at Berkeley, and he arrived late for a class, and the professor used to write down homework problems on one side. And so he quickly wrote down the homework problem, and then later on in his memoir he said that I do recall that the problems were more challenging than usual, right? And then he submitted it in the next week, and after that his professor called him because he had not put up those problems as a homework problem. He had put it up as an example of a problem that had not been solved yet, right? And just because he didn't know it had not been solved, he thought it was a homework problem, he sat and solved it, right? So who knows? I mean, right now we think that these are not equal, but somebody might come up with a solution.
So maybe I will like to add.
Yeah.
There are two names I think we should mention. Professor Ketan Mulmule and Milind Sohni.
Mm-hmm.
So in 2001, they came up with a result which is called as Mulmule-Sohni something like theorem or something like that.
Okay.
So they gave a precondition to solve P equal to NP
Oh, okay.
in geometric algorithms.
Right.
And there are workshops which happened in US, even in MIT,
Mm-hmm.
on Mulmule-Sohni result.
Okay. Okay.
Milind Sohni belongs of course to IIT Bombay, and Ketan Mulmule is University of Chicago, and in those days he was a visiting professor in IIT Bombay.
Okay.
So they worked together. One of my classmates incidentally was doing PhD with them. Then on this problem, then he left. But 2001 or 2, that result has come. So
Okay. I did not know this. I will look it up. Is this the spelling?
Mulmule, M-U-L-M-U-L-E-Y.
Yeah.
And
And
Sohni, Milind Sohni.
S-O-H-W or S-O-H-N-I?
S-O-N-I.
S-O-H-O-N-I.
He's
Okay.
still there in IIT Bombay.
Got it.
So there is a result. And second thing, because there are physicists over here, second thing happened in 2011. This person called Vinay Devalikar.
Yeah.
He proposed, he used statistical physics to prove P equal to NP.
Yeah. Yeah.
And then it was crowdsourced.
It was. Yeah. Yeah.
And then who is that guy from UCLA, the famous mathematician? He and the MIT guy. These two people kind of after 3 days they proved that is wrong.
There was a problem with that. I remember when it came out, and there was a lot of.
What is that name?
I know that the Australian
Tau something.
and Terence Tao. Yeah.
So he
Yeah.
and there was another guy in MIT. They kind of independently showed that
Showed,
it
yeah,
was not
yeah.
correct. But that was the first time when statistical physics was used in computer science. for
Yeah.
that time.
And you'll see how physics is used in some of the stuff we're going to talk about now as well. But thanks for this. I didn't know about the Mulmule-Sohni thing. I'll have to look it up.
So
Yeah.
eventually, when the Vinay Devalikar gave that result, the first thing I think Terence Tao or that MIT guy asked was, does it satisfy Mulmule-Sohni?
Yeah.
thing?
Yeah.
That was
The starting. Yeah. Yeah.
It didn't. So then they got the idea.
Right. Okay. So out here, there's one more kind of group of problems that it's not classically defined, but we can call it NP intermediate, right? So these are problems that have not been shown to be NP hard, but not been shown to be NP either, right? And these are typically problems, well, not typically, a large part of problems that can be solved using BPP, right? Bounded error polynomial time, are thought to actually belong in P. Those are problems that are NP intermediate. So for example, we talked about this last time, whether a number is prime or not, right? We had a probabilistic approach for it before, but then AKS showed that it can be done in polynomial time, right? Another example of this is graph isomorphism. So if you have two graphs and they can be oriented in many different ways, are they actually the same graph or not? Right. So we don't have a polynomial time algorithm for it. We have a algorithm that is very, very close to polynomial. It takes something raised to log n. So it's very close to polynomial, but it's not been proven to be NP hard. We haven't been able to do a reduction to NP hard, right? Factorization is another very interesting problem. So primes was given a number, is it a prime number or not? Factorization is given a number, can you split it into its prime factors, right? That so far we do not have a polynomial time algorithm for it, which is a good thing, and that's the reason why factorization is used as a property in most of the encryption schemes that we have. Not most, in like RSA and stuff like that, right? The fact that we cannot factor something in polynomial time is what makes encryption as powerful as it is. If we could, then that would break. But we haven't shown that factorization can be reduced to other problems in NP hard can be reduced to SAT. So that is an example, NP intermediate problem, and that is a problem that has been solved or can be solved using a quantum computer, using what is called Shor's algorithm, right? So I was going to end with this, but let me say this upfront itself. People believe that, oh, quantum computing is very, very powerful. It can solve a lot of problems that take exponential time. That is not correct. Quantum computing cannot solve these problems, NP hard problems. They cannot solve cannot solve in polynomial time, right? But they can be used to solve problems that are NP intermediate.
Intersection of
Not intersection, so they are neither in P nor in NP hard, so it's like a set difference, right? So you can verify the solution in polynomial time, but you can't, we don't have a polynomial time algorithm for it. Okay, so in order to make, to start talking about, so this is kind of the picture of computational complexity in the classical computing world, all right? In order to understand the kinds of problems that can be solved using quantum computation, we need to have something similar for quantum computation. I just repeated myself. But we need something similar. We need to have the notion of a Turing machine, and we need to understand the kinds of problems, and therefore which problems will be amenable to quantum computation and which will be not, right? So in the subsequent, I'm going to talk about 2 or 3 things. I'm going to focus on 2 problems which define kind of a quantum equivalence to this, and then we are going to talk about a few classes that are of problems that are similar to this, all right? So to start with,
So firstly, we have to identify whether the problem is NP intermediate or not. If it is, then we should go to RUSI.
it's a bit more nuanced than that. We'll come to that. Yeah. So let me start with. I won't talk about this too much, but just in broad terms, this is for all x, right? There are many ways of interpreting that. You can say for every x and so on. So that is what is called a universal quantifier in set theory. This is called an existential quantifier. There exists x such that something, right? So when we talk about 3-SAT, what we are saying is I have a Boolean formula of Boolean variables, of predicates, right? And that's all that we talk about. But implicitly, what we are saying is that there exists an x1, there exists an x2, there exists an x3, and so such that this formula evaluates to true, right? So I just want to bring in that aspect of the universal quantifier out here. So we're saying there exists these variables such that this formula will evaluate to true, or maybe it doesn't. That is, there's this implicit part that we tend to that we tend to elide over.
What do you mean by that it will evaluate by?
It will evaluate to a true. So if this is my formula,
Evaluate to a true.
yeah. So there is some value for x1, some value for x2 and x3.
You will get 1 or 2.
When I plug it into this, it will evaluate to a true. Right? So these are exactly equivalent. I'm just rewriting this in terms of these quantifiers. Is that? Yeah, okay.
You are saying that statement will be interpreted by these mathematical symbols, right?
Yes, but it gets a bit more intricate than that. So this is a problem that requires exponential to solve, right? Here is a problem that takes even more time to solve. So if I replace, this is an existential quantifier. It's saying there exists an x such that. What happens if I replace that with a other quantifier? If I say there exists an x1 for all x2, there exists an x3 such that this evaluates to a true, right? What does this mean? Take an example. Let's say we are playing a game of chess, right? What this would say, I think okay. What this is saying is, if I make a move, right, and then my opponent is allowed to make any move, right? So given my move, my opponent can make any move, right? And then based on the move, I will respond, right? In that scenario, is it possible that this evaluates to a true? Or in terms of the game that I was saying, I make a move, no matter what my opponent does, I will have a response such that I will win this game. Make sense? Right? Between these two, so this is what is called a QBF. That was SAT or 3-SAT. Right? 3-SAT is a special version of SAT, and you can convert any SAT formula to a 3-SAT form as well. Which one do you think is more complex? Why?
X2 set is more.
The what is more?
X2.
X2 is more.
For every x2 we need to solve.
For every x2 we need to. Okay, does this, okay, so this, does everyone agree QPF is in some way more complex than SAT? Anyone disagree? Okay. So one of the things that we started out with was the class P and NP, right? And what was NP? I should be able to verify the solution in polynomial time, right? So if belongs to NP, you say yes, it's verifiable, okay. Any other?
We have to check for all possible x2.
Exactly.
Possible whatever x4 and things
Yeah.
like that. So number of options increase.
It not just increases. So the possible solution that I would give would be a particular value for x1 and x3, but a whole bunch of values for x2.
That can be exponential.
That can be exponential. So even to verify it, the input that I get itself is exponential, right? So I can't, it doesn't even belong in P, right? So
X2 is bound.
x2 is, it's not, it's like for all x2, right?
You mean
So,
to say bound in NP?
what, say that again?
It is a limited set. That is
You
what I
happen
mean.
to say that?
Even if Boolean, right, I have two choices out here, right? There will be an x4 which I have two choices. There will be an x6 where I have two choices. So the number of combinations of those is also exponential. So even if it is limited, it's still, right? So this is an example of a problem that doesn't even fit into P, right? Sorry, into N, thank you, into NP, right? And there's multiple ways of thinking about this. So out here we're saying, you know, does there exist an x1, x2 and x3 such that the formula is true? Out here we're saying, does there exist an x1 similar to that such that for every x2, does there exist an x3 that makes the formula true, right? So if you think about it a bit deeper, basically out here what we're asking is there a combination of the x's that satisfy the formula? Out here we are talking about strategies, right? And then that becomes an exponential thing. So that is the kind of reason why QBF is not in P, right?
What about deep seek? They play chess and then they won the game. Deep seek is chess thing. How do they do that? This kind of thing.
So that is exhaustive search with a lot of pruning algorithms in there. Deep Blue, I think.
This chess thing. That
So in 97, 96 and 97, IBM developed Deep Blue, which was the first computer to defeat a reigning world champion, chess champion. It took until 2016 for AlphaGo to defeat the reigning Go world champion.
Stockfish. And chess it was stockfish.
Yeah, now like you have a very powerful chess playing programs, right, that run on your laptop, right, that are probably at grandmaster level, right? But how do they work? They are basically doing exhaustive search, right? But they're doing all of it in parallel. So that's
Accident,
yeah,
The Deep Blue is exhaustive search.
yeah,
DeepMind they have introduced reinforcement learning,
right.
which is not perhaps the exhaustive search. They are like playing a game.
Yeah.
And
So actually not DeepMind, Alpha Chess.
but Alpha was
Right.
from DeepMind only.
Yeah, so their whole series of like Alpha Chess, Alpha Go. So the way it is trained is exactly what you said. They basically have it play against itself, and therefore they've come up with new opening strategies, new ways of playing that were not possible before at all.
That's the one which was used later on for protein folding.
Yes.
Yes, DeepMind. Yeah,
DeepMind, yes.
yeah. So my one claim to fame is when I was doing my PhD, I did an internship at Watson, and in our orientation, this poor chap said that. So this was in 2000 or no 2001 or 2002, I don't remember. So relatively close to 97, and the poor chap said that the computer that beat Kasparov, we have a stripped down version of it at Watson. So for the next 2 months, I was after him. Give me access. Give me access.
There is a folklore that there was
The controversy, right?
the move that Fox Kasparov
Yeah,
was
yeah.
a computer bug,
Yeah.
and it was known in the press conference,
Right.
last press conference. The IBM declared that it was a computer bug.
So the thing was, Kasparov kept insisting that show me the search tree, the eval tree,
Yeah, no,
and they refused to do it.
It
Yeah.
seems what happened was there was some lazy programmer, and out of so many moves, if it couldn't get the correct move in so much time, they
It
would
would-
do some random move,
Okay.
and that foxed everyone. And then he was psyched out.
Right.
In the last press conference, then it was asked what happened. So
Yeah.
IBM people said that that was a bug. The next day, Kasparov said, "I want to play with
A
the
rematch.
And
Yeah.
these IBM people said that that computer does not exist. We are dismantling it now. You can't play it."
Yeah. No, so the thing is, it was like a 64-way parallel machine. They just had a one with like 16 nodes that kept
No,
running.
it's stripped down. So
Yeah.
That's why they said the same one is
Yeah. So anyway, so that was like I first spent the remainder of my internship, which is why I didn't do very well out there, playing chess against it, and of course the score was 0 for me and everything for the other. but anyway, that is my one claim to fame. Okay, is QBF in NP? Is it in P space? Can it run in a limit in a polynomial amount of space, or does it require an exponential amount of space?
But neither NP nor.
No, the space.
it runs.
It runs because you're just cycling through different values of x2 and x4, so you don't need that much this thing. Okay,
QBF is not NP.
it's not in NP at all.
What definition says you can check it in polynomial time.
QBF you can't, right?
But a solution you have, you put in the
But what is the size of the solution? Because it is for all x2.
one solution.
for all x2. So if you want to give it one solution, you can specify x1 and x3, but you still have to try.
So SAT is NP.
SAT is NP. Yeah.
There is another way perhaps to look at this. If I want that those such, I need to give a counter example.
Mm-hmm.
That
Counter example to?
counter example to cubic. Because there is for all.
Yeah. Mm-hmm.
Right?
Okay.
So here we are asking whether it satisfies. So because it and there is a for all.
Right.
So I say that I come up with at least one x2
For which it doesn't satisfy.
Now to find this out is essentially NP complete. Because you are asking other questions.
Right. No, I'm trying to formulate in these terms. So if I take the negation of this, right?
It's not negation. It's like a counter. How do you say?
It's not a contrapositive.
It's not counter.
It's not contrapositive. I'll have to think about it. I see where you're going. I'm trying to think whether it. So there's four of those, right? There's the inverse, contrapositive, and then there's two others which I've forgotten. And then so for example, in any set theoretical approach, if you prove the contrapositive, that's equivalent to proving the original. And then if you prove the inverse, it's equivalent to proving the other one, which I've forgotten. So that's basically what I'm trying to formulate what you said in those terms to see whether that matches. But I'll have to think about it. Yeah. Okay. So okay. This is diagram that I was talking about. So we have NP. I drew NP complete completely inside NP. It's actually a little bit outside. And then these are the NP intermediate ones. Factorization is a great example of that. And for factorization, there is actually something called Shor's algorithm, right? And the way that works is it looks basically a period finding algorithm. So factorization itself has a little bit of structure. It has a periodicity. That is what Shor's algorithm is searching for, right? This makes more sense when you actually look at Shor's algorithm. But this is an example where if you go from an exponential time to a polynomial time algorithm, okay? In contrast, there is an algorithm called Grover's algorithm, and I'll tell you the setup for that. You have a long list of values, and you want to search for one value in that. Think of an array, and you're searching for a value. So this is unsorted, it has no order. So all you can do is go through it sequentially, right? So your running time is proportional to the length of the array. And typically the way we count it is in terms of the number of bits required to represent the elements in there, and therefore it becomes 2 raised to n problem. What Grover's algorithm does is it gives us a running time that is the square root of that, okay? And this is important because what that is if my running time is exponential, what is the square root of an exponential? If my running time is 2 raised to n, uska square root is? It is 2 raised to n upon 2, it is still exponential, right? So while you can get a very good speed up with quantum computation in that case, it is still exponential. It hasn't really achieved a whole lot. Shor's algorithm on the other hand actually brings it down from running time to polynomial running time, right? And Shor's algorithm belongs to this class that is called BQP, right? That is supposed to be an exclamation point, it's not BQP1. Okay, so what is the hierarchy that we have so far? BPP is bounded error polynomial time, and examples of that are verifying matrix multiplication, or the primality, checking if a number is prime or not. P space is on this side and exp space is beyond this, right? Exp time also. BP is bounded error quantum polynomial time, right? And this is a very interesting class because think about the way we've been talking about quantum computation, right? It's always do all of these operations, you have these quantum measurement. And if you have, one state 1, A2, state 2 all the way to an minus 1, you get one of them at the output with a particular probability, right? So you may not get the actual answer. You've got to run it multiple times. This kind of fits into the BQP, the bounded error quantum polynomial time, fits into the model that we've been talking about quantum computation to begin with. There is a model called exact quantum polynomial, but out there the assumption is that when you do all your processing, out of all the states, one state has the maximum value, everything else has 0, right? And it's very rare that we end up with something like that. So usually when we talk about quantum algorithms, we're talking about something that is out here, BQP, right? So now the question is, how does BQP intersect with this model? How do we find out what the overlap is, if there is an overlap? Of course, there's an overlap because we have Shor's algorithm, right? But is all of this included in BQP, or is BQP a subset out here? Still an open question. Right now we believe that BQP is a superset of BPP, and BPP typically are these NP intermediate problems. For sure, NP complete is not a BQP problem, or they do not overlap, because even if they overlapped, we solve one NP complete problem, we can solve them all. Okay. Okay. So the aspect that I talked about with verification, right? I give a certificate, and then in polynomial time I use a Turing machine to validate whether that answer is correct or not, right? That is captured in something called the Merlin-Arthur. So Merlin, so if you go back to whatever century England, and you had King Arthur and Knights of the Round Table. So Arthur's big advisor was a wizard called Merlin, right? So it's Merlin and Arthur. That whole verification business is encapsulated in something called Quantum Merlin-Arthur protocol. So in a classical context, Merlin is providing a specific solution. So for 3-SAT, it's saying take x1, make it true, take x2, make it true, take x3, make it false, take x4, set the values. So it gives those, and then we have to verify as Arthur whether that formula evaluates to a true or false. Q kya hoga? Merlin is providing a bit or a set of qubits, right? And Arthur is going to run them on a quantum machine. He's going to evaluate the output, and then he's going to see whether the output matches what it is supposed to be or not. Okay? Do you guys immediately see the problem out here? In what we talked about, right? At the output, you have a probability distribution. You have the probability amplitudes across all the states, right? And one of them gets selected. That may or may not be the right answer. How do you verify whether this certificate was correct or not? You run it multiple times, right? So then you start developing, like the circuit that you had shown, you run it 500 times and you start seeing the probability distribution. But then this hits us, because if Merlin only provides the qubit once, we can't run it multiple times, right? So, so there is a little bit of qualification around this QMA protocol, in that maybe Merlin is providing 1,000 copies, right, claiming that this solves the problem. Right? But that's something that you guys should be aware of. But anyway, so QMA forms a class similar to NP, right? QMA forms a class of problems where, given a input set of a qubit set of qubits, right, we can verify the solution on a quantum platform in polynomial. Okay. So this is where we start drawing parallels to the classical world. The classical world, we had class NP where we can verify the solution. Out here we have the class QMA, where we can verify the solution. The last piece that we are missing is, in the classical world, our starting point, the first problem that was shown to be NP hard was SAT, right? What is the equivalent problem out here? Now this is where I'm just going to tell you what the problem is. I lay no claim to being able to explain it or even understanding it myself, right? So maybe you guys can pitch it here. Something called a LHP, local Hamilton problem, and it does something with calculating the lowest energy states of some things which I do not understand. So I made a few notes. SAT we've talked about multiple times. Is there a set of true or false values that satisfy a bunch of clauses? Out here we're saying, is there a quantum state that satisfies a collection of local energy constraints? So I don't know if you guys have any insight into this or not. I don't. I'm not. I looked at all the description, but I didn't really go into the details out here. What I want to point out is, similar to NP completeness, where we have to have verifiability, show the problem belongs to P, and hardness. So hardness is basically saying that if I have a new problem and I want to show that it is NP hard, I have to show that every existing NP hard problem can be transformed into this in polynomial time. That is what the importance of this problem comes from there. If I want to say that I can solve in polynomial time on a quantum machine, I need to be able to show that I can transform it into an instance of LHP in polynomial time.
Is there any other NP problem or P problem which can be transformed in polynomial time?
In classical, or in classical there are lots. I mean there's so 3 SAT, there is subset sum. So if you have a bunch of numbers,
In that case, how can I prove that a particular problem is NP hard
because I can transform them into other NP hard problems in polynomial time.
But can you do the same thing with some other NP problem that I can?
So the ones that I can are NP hard, the ones where I cannot are NP intermediate. So for example, factorization, there are graph isomorphism, right? So we don't have polynomial time algorithms for that, but we haven't shown that they're NP hard. So those are problems that are, who was that? Trishanku, right? Adhantari is neither going to heaven nor falling to earth. Trishanku, yeah. Okay, so if I say that, and this is what I want, have you really capture, right? Classical computing, this beautiful theory of P, NP, and a lot of other stuff also, but primarily P versus NP. If a problem is NP complete, we can verify it in polynomial, and we can do a polynomial time reduction from any other NP hard problem, right? So QMA complete is the same, right? And this actually, the fact that, again, like I said, I don't pretend to understand this LHP problem, but if I can transform an LHP into a problem instance that I have, then I can solve that using a quantum computer with a good speed up. So for example, and I have a list out here, I'll come back to this. If I'm doing quantum simulations, I will get huge speed on a quantum computer. And this is what Feynman was talking about when he said that you want to, and okay, this is important, I want to talk about quantum simulation. So if we run it on a classical computer, it takes not just 2 raised to n, but 2 raised to 2 raised to n, right? Whereas on a quantum computer, that state space just collapses, right? And what Feynman was saying is exactly this: if you want to simulate a particular model, simulate it on a computational model that reflects what you're trying to simulate. If you want to do quantum simulations, if you want to look at how electrons or not protein, but how proteins dock, use a quantum simulator, it's much more efficient, right? If you're doing a problem that has some kind algebraic structure where if you can do kind of period finding that will lead you to the solution, it's great. This is exactly what Shor's algorithm does, right? And to extend this a little bit, when we talk about PKC or PQC, sorry, post quantum cryptography, right? What are they talking about? No. So,
Modulo operation. So
actually, very specifically not modulo operations. So what they're doing is they're using branches of mathematics which do not have any periodicity. So post-quantum cryptography is still very much grounded in classical mathematics. It's using algorithms where if there is no period, so you can't find it, so you cannot use quantum computing to solve it. This is what PKC is. So it's much classical, it's not quantum, but it is at least so far resistant to breaking in quantum computation. That's the idea behind PKC, right? Optimization. So you'll quantum linear. If you want to solve AX equal to B, right, where A is a very sparse matrix. There are a whole bunch of conditions around that. But it turns out that would well, you were able to figure out how to encode that matrix, right? This part, the optimization part, is what leads to quantum machine learning, right? We don't have time now, but and I think I've gone over time also. But there's this very interesting loop that would be completely insane in a classical sense, but in a quantum sense, it makes a lot of in a quantum world, it makes a lot of sense. So, for example, in regular machine learning, we are like if you have a neural network, you're calculating the gradient of every weight with respect to the loss at the output, right? That's easy to do in a quantum in a classical setup, right? How do you do that in a quantum setup? So the trick is you set it up with a bunch of weights. You do a forward pass, and for every weight you do delta W minus delta W, right? You calculate at the output. Then you calculate the gradient by saying, loss 1 minus loss 2 upon 1 plus W2 or upon 2 delta W, right? And if you were to do this, so you do this for every W, right? If you were to propose doing this in a classical world, it would make no sense at all because the computation is so much. But in a quantum world, it makes a lot of sense. So fast that benefit, that speed up more than outweighs the fact that you're doing it so many times, right? So that's kind of one a quantum machine learning works more to it. The other thing that I find very interesting that I really like is, and to machine learning as well, if you have a problem where you're not interested in the absolute minimum value of your loss function, but you want to be in the region of your loss function, that is where computing makes a lot of sense because you get a distribution if you run it multiple times, right? If you run it a lot of times, you'll get the absolute minimum, but you don't really want that. You just want something that is in the region. So then this works very well.
You mean local minima as you say?
So I think quantum is better at avoiding local minima. But at the global minima, you get closer and closer. Typically, your gradients out a lot, right? As long as you want the absolute minimum value, this works.
Pareto
Right.
optimum or something.
That's a different, that's a slightly different topic. Yeah. All right. Any questions?
Just a comment.
Yes.
I mean, place quantum simulation. The famous none of them are really easy.
I find that funny.
So that's very tough. People talk about using minimization techniques, optimization techniques basically for quantum mechanics, what
Yeah.
we call as a proper quantum mechanics.
Yeah.
And this process has not been yet at the level
Yeah.
where one would, while the other algorithms, they are absolutely non-quantum.
Yeah.
So I want to see how a multiparticle die. Evolution. This was very simple concept.
Yeah.
No breakthrough.
Yeah. And that's the part I find when we talk about quantum computation, we start with Feynman's quote, right? And then we talk about Deutsche, Grover's, Schur's algorithm, and all of the other stuff. We don't talk about the actual quantum simulation that he was referring to. So that's it's yeah, it's a source of endless amusement to me. Yeah.
PQC problem, post-quantum
Cryptography.
NP or intermediate NP.
No, that would be like EXP time. So as far, well, oh, okay, hang on. I spoke too soon. That would be NP. Yeah, because if you give me two numbers,
Then can be solved in quantum.
no, that's the whole point, right? Actually, it's good to set that up. So quantum systems, right, will speak in scenarios where you have some kind of structure, right? The point of thing is called lattice-based cryptography. I've not yet looked at that too much. But like if you look at RSA that is based on factorization, there's also something called elliptic curve cryptography, right? Which is you can crack that using quantum computers, right? Lattice-based cryptography, because it does not have the just because, and that's kind of the point, right? This I have, yeah. So even so, for problems that are NP complete, they are not applicable to quantum computing because they don't have the structure that a quantum algorithm would be able to execute, like the periodicity that we were talking about. They are not optimization problems necessarily, or not the optimization problems that have a good structure, right? So I think you asked, Professor Zog asked this, different kinds of NP complete problems. You have stuff like salesman, right? Or and this is where again things are very funny. You have something called cycle. You have a graph. You to the other without repetition. That's a ham cycle. Or if you end somewhere else, but you've traversed everything, that's a ham path, right? So is used to this. And then when we were talking quantum computing, saying, oh, the Hamiltonian, we were immediately thinking about ham cycle and ham path. They're different things. Okay, my point is that NP complete problems that we have do not have structure that can be exploited by we know of so far, right? The other ones are these ones that are NP intermediate. Does that answer your question? Right? No. So it's a hypothesis. It's one of those. So even P versus NP. Believe P is a subset of NP, but yeah, it probably falls into the Gödel's, something you prove not disprove. Right? So yeah, so that was good because it didn't wasn't NP, right? And so even factorization, right, is not NP hard, and lo and behold, Schur's algorithm solves factorization problem. All right. So the whole point of these two sessions was to kind of begin, everything obviously, to have you guys see the overlap or the similarity of how we can put quantum computation on a good theoretical framework, just how classical computation has the structure, right? And draw equivalences between them. And in classical computation as well, this is theoretical, but it's not. Because if you're working on a problem and you can show where it is, that actually leads to ideas for solutions, for efficient solutions. Similarly, quantum can show something may complete it, or it already starts giving you a lot of clues about how to go about solving it or not solving it. All right?
A simple question that's known to many. I take a graph structure in 3 dimensions, and number of pages.
Yeah.
This is a definition of cluster of atoms.
Okay.
3 dimensions.
Yeah.
Actually, onto a graph,
Sure.
where is between two atoms.
The weight on the edge.
Yeah,
Okay.
weighted in some way.
Yeah.
Now I have a following problem which is still not resolved. So I have two sectors. Let's say I want to know what is the so-called fingerprinting distance, but I want to them the two clusters to be identical but rotated in an arbitrary way. For me, they are same.
Yeah.
Find it really. I mean, there are ways of doing it, which we do. But the two clusters, the same number.
Yes. Yes.
The which vertical as a 0, which is distance. Have some of this
Yeah.
distance.
So this is a problem. This is a problem that is called graph isomorphism.
Correct.
Yeah.
Are there easy?
So that is intermediate.
Okay.
As far as I know, running time is something like it's a 2 log of n to the base epsilon. So it's not exponential. So if it were 2 raised to n, then that is exponential. Log of n to the base epsilon, and there has been work that exponent. It squarely. So we've not shown that it's an NP hard, right? We don't have a polynomial time algorithm for it, but it is what we are calling NP intermediate. So no, that's a different thing. So if they are isomorphic, then the distance is 0. Yeah. No, but that's the thing. If it's isomorphic, the distance is 0, right? If it is, so what I was talking about, it will give you a yes or no answer. Is it isomorphic or not? If it's not isomorphic, then we can talk about there's a difference.
I think and one additional computing weight changes. Is not there
In the regular isomorph, yeah, we are just looking at the structure.
That's because if I symmetrically cluster, it's because if I
Yeah.
put a
So, and
Another thing comes from here. There are isomorphs which are possible.
right.
Because the which one here the simpler that structure is identical. So
Yeah.
that then you are asking more.
And there are ways of accounting those weights as well. No, but like if we solve simple problem, we can move to the difficult.
problem in the machine learning algorithms that we use very routinely, and the two clusters. I just don't.
Are they actually the same or not? Yeah.
Solve by doing typically doing transformations using the symmetry angular momentum theory. But that's clumsy. I mean, what you were talking, at least at a theoretical level, is very practical solution. I don't know.
Well,
There are
result, I don't know the actual algorithm. So if we look at the algorithm, it might be as right now, but yeah.
quantum computer. I mean, classical computers, we have many,
Right.
more, if it is,
The quantum version of a, wow. Okay.
I don't know how, but
Right.
in the sense that it would be interesting if there is such a quantum version.
Yeah, yeah.
Because it has many applications, so you can think of.
So if you have a weight with a, or an edge with a certain capacity,
That is what.
right?
Capacity is my weight.
Right, right. So the way Fulkerson work is by incrementally putting more uh, goods through uh, no quantum.
No, you have to.
Or we try to model it with entanglement.
this is
Yeah.
a very burning problem.
Yeah.
I think any of the terms need to be solved
Yeah.
because in addition of the too much.
Honestly, I feel quantum computers have been a lot easier if we weren't using terms like qubits and gates, because because no, the tendency is to equate them to what we already know, and it's not. It's completely different. Uh, Saying we need to stop. Let's have, happy to continue the conversation. Also, please do the evaluation. Let's talk about it. You.
talk on quantum algorithms only, but then I saw this lecture, description of lectures, and that my in front of my lectures this information was written. So I thought that I could speak a little bit about this information aspect. It's quite elementary. I'll be speaking, and it's not as as complex as the previous lecture, where the computation and the relation of computation and information and all these things were discussed. Where is the? I need a duster. Duster is not there. Yesterday there were 2 dusters, but डस्टर नहीं है इथे इथे कुठे डस्टर नाही खाली आहे का नाही खाली नाही okay so I mean what I intend to do is to give you an idea of how a unit of information is classically defined and how a unit of information is defined quantum mechanically. So yeah नाही येत आहे आवाज. Hello, hello, no.
Hello, check. Hello.
So I mean, initially I was just thinking that I will cover some quantum algorithms in this lecture, but now I intend to do partially something on information because it seems that it is I was expected of saying something about information. So in the course of my lecture, I'll have to define what are called mixed states, but I can sail through it in the context of information as I want. So suppose you have an object and some characteristic of an object, and if you have some partial information on those characteristics, and that characteristics may have many values, so some information, not the information, complete information means you know the value of that characteristic, you know it, that object has, okay, that object has some, it could be some spin, it could be something, any other thing, it could be simply a color or whatever that is. So but you can just have a information like some 3 colors, and you can say that you may say that only its color is one of these 3 or 4 or whatever. So then you can, the only thing that you can do is to make a guess using some information on that shop. If you know that the shop keeps red type of cloth more, then you have said you can make a guess that it might be red and something like that. So to quantify this idea, the only thing is that you have to assign probabilities for various kinds of outcomes or various values of that particular characteristic, and therefore you end up with a kind of probability distribution over its values. Okay, so okay, so and this probability distribution will change with the kind of information that you have. For example, I have some kind of information, I define some kind of probability distribution over the values of that characteristic. But then suppose I extract the exact value of the characteristic, then the probability distribution will be singular. It will have probability 1 at that particular value and 0 otherwise. So depending on what kind of information that I have, what is the amount of information I have, the probability will depend on that, what kind of probability you assign, what is the probability distribution, and so on. So now suppose we lock on to a single bit. Okay, so it has only two values, 0 and 1. And suppose you assign some probabilities, say P1 and P2. To these values. The question is, in this situation, how can I estimate the amount of information that I have? And as yesterday it was pointed out, if I measure that, measure that bit, and if P1 is less than P2, before measuring I have assigned P1 and P2 such that P1 is less than P2, and after extracting the bit it turns out to be 0 after extraction. Okay, then I have my contention is I have gain. One has to talk about the gain in information. So how much information do I gain? I gain more information as compared to the other possibility. So if I assign P1 less than P2, and that is P2 is the probability for 1, P1 is the probability for 0, and after measuring it, after extracting the exact value of that bit, if it turns out to be 1, then the amount of information I gain is less than otherwise. That if P1 is less than P2 and if the extracted value is 0, then I gain more information than the eventuality of getting 1 out of it.
Higher probability means less information.
Less probability means higher information.
Gain.
Yeah, here P1 less than P2. No? This is what I assigned before measuring it. Okay, from whatever I know about it, I use something, and then this is my guess, so I get P1 less than P2. Okay, now I actually measure it and I find out the state of that bit. What is this? What is the value stored actually in that bit? Okay. Then if it turns out to be 0, which corresponds to the less probability that I have already assigned, then I gain more information. It is, one talks about the gain in information. There is nothing like, storage of information that, that is what you can measure or what you can, experience is how much information that you gain by a certain process. So this is what I do. So now I have to model it somehow. So the simplest model is that let me define the information gained is just as so this is now, if P1 is less than P2, then this is 1 upon P1 is greater than 1 upon P2. So the amount of information I gain is simply the reciprocal. Okay, let us try out this, let it be my model here. So now okay, so now let's go to 2 bits. So these are the values. How do I get to these values? I have to extract them independently. These bits are not interacting, or they are not, the value of one bit is not influencing the value of the other bit in any way. They are independent objects. So if I, to get these, to get any one of these options, what I have to do is I have to independently measure these 2 bits. Therefore, the information I gain must be just the must depend on the information that I gain while measuring a single bit, because I am measuring a single bit each time, I mean independently. Okay. So these are independent events. These measurements are independent events. Therefore, by elementary law of probability, this probability of any one such event is simply, I mean, probability is P1 into P2, sorry. So probability is P1 into P2, okay. And by my law of reciprocity, the information I gain is P1, P2. Okay. So this is, suppose I write P0. So information I gain for the first option is P01, P1 upon P01, P02. Information I gain is P11, I mean P1, 0, P21, P11, P20, and P11 and P2. When these are the corresponding probabilities of extracting these. So that means the probability for extracting for the first qubit is P10 and P20, and for the second qubit I assign P1. So with this assignment of probabilities, these are the informations. So that means you take this P10, P20. This I can write 1 upon, I mean trivial, 1 upon P00, I mean P01 into 1 upon P20, P02. So this is a product. This is the information I gain by extracting the value of the first bit. This is the information I gain by extracting the value of the second bit, and therefore the total information by this particular method is simply the product of two informations. But this is something that you don't expect. When I get information on some event or some kind of object or whatever it is, and I gain the information by knowing the value of some other parameter or something like that, then I expect that the total information I gain must be the addition of these two information. I mean, I get the, it's not a product. So how to convert this product into additions? Take logs to the base 2. Okay. So this is, so information I gain is minus log to the base 2 of P1 0, for example here, minus log to the base 2 P I mean P0 again P02. Okay. So in order to get the measure of the information, the total information that I get, I take the average. What is the average information I get? So that is just multiply by the probabilities and add them. So this is minus P10 log to the base 2 P10 minus P20 log to the base 2 P20. This is the information I gain in this particular event. Okay. So, and this is the average information. So now suppose I have a, now so this is the, so for going over to the single bit, I get, suppose P and P1 and P2 are the probabilities I assign to the values of the single bit, then I get say P1 log to the base 2 P1 minus P2 log to the base 2 P2. Okay, so now suppose initially I don't have any information. I mean, in order to make any guess or assign any probabilities, I need to know something about that. I mean, but suppose I don't have any idea about it, about the value of that bit. Okay, then both values are equally likely. That means probabilities are same, equal, and therefore it is half. So I get minus 1/2 log to P1, I mean sorry, 1 half minus 1 half log to the base 2, then 1 half, and that is equal to 1. You can calculate it. So this is 1. So this defines a unit of information. So what is the unit of information? I have a bit, I mean, two-valued object, and the kind of information I gain when initially I don't have any idea of the what are the values. So that is the maximum information that you can gain out of a single bit, and that is my unit of information, and that I call 1 bit of information. That's a 1 bit of information. Okay. Now if I have now, suppose I have not only 2 but there are many options, then the information that I gain is summation of pi log to the base 2 pi, I running from 1 to n, whatever, if there are n options. So this is the total information that I gain when I assign probabilities to all options and so on. Now you have to look at it in the reverse way. See, gain in information is the same as the amount of ignorance that I had before I measure it. I measure the thing, I get the value, so I gain the information and that we have seen how to account for it. But it's the same as the kind of the amount of ignorance that I had before I measure it. Okay, so when you look at it in that way, you define it to be the entropy. This is the Shannon entropy or the information entropy about that particular process. So now let us go to the quantum version. This is my classical thing. Okay, so what I'm looking for, I'm interested in the gain in information from a quantum system in my world. That is an information which I can read and which I can swallow and I can use it for any other purposes. I mean, before that, whatever information is there is inaccessible to me. I mean, there is no point in talking about that information because I don't know how to make use of that information. Okay, so that means measurement plays a important role, because measurement is the only way of transforming that information contained in the superposition of whatever input state to the output. Okay, that will be one of the eigenstates. So I am measuring certain observable of the system, and it is the eigenbasis say psi I, whatever I running from 1 to n, and my state is state is summation over I psi I psi, this is the coefficient because this is orthonormal. So these are the coefficient if this basis is orthonormal, and into psi I. So this is, I will write like this, psi I into bracket psi I psi some more I. This is exactly how we proved this resolution of identity and so on. That's fine. So okay. So now what I do is, in order to get the amount of information that I could extract out of this superposition? That is the question. So what I do a trick. What I do is I make a measurement, but I do not record its result. I don't know the result. Measurement is made, but the result is not. I mean, I know the result is one of the eigenstates, but which eigenstate I don't know. So what do I know? I know that the state of the system has to be in one of the eigenstates of that operator or that particular observable with probability. What is the probability? Probability is the mod square of the amplitude of this. Okay. So this is exactly the kind of ensemble that I have. So this is the ensemble. It could be psi I, comma, mod alpha I square. I mean, yeah. Okay. So now, how to model this? This from the ensemble. How do I model this about the system? That way is so-called in the following way. That what you do is you define a convex combination of in the following way psi. This is the projector of every eigenstate multiplied by mod alpha I square sum over I. This is called a density operator. And typically denoted by rho. This is not a superposition. These probabilities, now after I make the measurement, these probabilities come out of my ignorance. I am ignorant because I have not recorded the result. And therefore what I can say is the state of the system could be ket psi 1 with probability mod alpha 1 square. State of the system could be state psi 2, state ket psi 2 with the probability mod alpha 2 square and so on. That's all that I have now. Okay. And therefore this corresponding state, so it is a kind of ensemble of pure states. These are the pure states, and I have an ensemble of pure states with the how do I define it? Take a pure state, attach the probability to it, and this is the ensemble. This is the ensemble, and I construct this particular. This is a convex combination because summation of I equal to 1. Such a combination is called convex combination. So I have a convex combination, and now this in this linear combination the coefficients are probabilities, not the amplitudes. This is not a superposition. This kind of state is generated because I don't have sufficient information to pinpoint the state. I don't have the sufficient information. This is the only way probability enters in classical world. Classical world is all deterministic. Absolutely, there is no problem. But you can probability does enter. For example, if my system is too large, then suppose Avogadro number of particles. I mean, it's impossible to pinpoint the state of every particle and do something about it and something like that. So you have to take resource to the probabilities there. As this is one instance where you can do it. You have to do it. So there are so many other instances in even the classical world where the probabilities enter, but they enter only via only one route. What is that route? Ignorance. That is insufficient information. You don't have the sufficient information to pinpoint everything, and therefore you have to take recourse to probabilities. And this is exactly happening here. I mean, I have an ensemble of pure states. Each pure state is capable of expressing itself in superposition. They are the elements of the state space, all these i's. But here what is happening is I have a collection of pure states which are elements of the Hilbert space or the state space of that system, and I know that the system is in one of these states, but which one I don't know. So I can just say that this could be, the system could be in, say, ket psi 1 in mod alpha 1 square with probability and things like that. Okay. Huh? Ensemble is a set. Yeah, ensemble is a, yeah, ensemble is, you know, point is that this ensemble is not a physical entity. It is like kind of a, I mean, you can say that it is my mental picture of what is happening. I mean, there is no physical way or actual way in practice to access this ensemble. This ensemble is a model which I am using to define this mixed state, and this mixed state is, I mean, is something real. I mean, you can do various things with mixed states.
Can we
Yes,
take
absolutely.
it as a that there are 2 points in the block sphere,
Hmm.
and it can be any of these.
Yeah,
With
yeah.
probability P1 and
Even
mod of alpha 1 is
yeah, yeah. I mean, block sphere, you want to impose it, there is
no,
no
just to
problem.
visualize that it can be either here or here.
But
Both are states, complete states.
no, no, but there you cannot superpose them. I mean, it's not a superposition of
This is
anything.
also a superposition. This
And each one is superposition of the basic states and all that. That's no problem.
you have to write it.
Yeah, yeah, but the mixed state is like this. Okay, and this is, remember, note that this is expressed in terms of the projectors. Not, I mean, I'm not writing this as some kind of sum. No, I'm not doing that. I'm using projectors, and I can use projectors because the other day I proved that all pure state quantum mechanics can be obtained by projectors. That is, the corresponding probabilities can be expressed. I mean, you can replace the ket by its projector and do everything that you can do with that ket. Okay, there is absolutely no problem. So I can do it. So this is what I do, and then okay. So this is an operator. I mean, now the state is being described in terms of an operator, and this density operator you can, I mean, this is the density operator, so you can diagonalize it or you can express it. You can use any arbitrary. It's an operator acting on the state space. So you can use some arbitrary orthonormal basis and set up its matrix. You know how to set up a matrix of an operator. So if you set up that matrix, you call it density matrix. Density matrix is the matrix of rho, this operator, with respect to some orthonormal basis, which you know how to set up a matrix for any operators. In the same way you can do it. Okay, so this is the density matrix. So now, well, so this, yeah, so this now gives me a device to, once I get hold of density operators, what I am getting hold of is these probabilities. This is very important. So if I set up the density operator, there are various means of finding out what the density operator is in various situations. So what I do is I take a density operator or a density matrix and diagonalize it, and then I get the diagonal elements like this after diagonalization and the eigenstates.
By diagonalization, you mean the equivalent
No, no,
only the
the,
diagonal element and make others zero. This is diagonalization. Or
you know how to diagonalize a matrix?
that's what.
That's it.
It's not like
Yeah, is a
zero.
matrix, you diagonalize it. So those are, what you get is the eigenstates of rho and eigenvalues of rho. So eigenvalues of rho are the probabilities.
We delta V Hermitian. U Hermitian.
Huh? What?
We diagonalize any matrix in
Huh?
classical, so we write U delta V Hermitian, something like that.
No, 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 no.
Orthonormal
So,
basis, and U and V are the matrices of orthonormal functions.
No, no, you can, there are certain matrices which cannot be diagonalized. That's what you are referring to. But we are not interested. These are all diagonalizable. There is absolutely no problem. Okay. So you can diagonalize these matrices and you will get these probabilities. So this gives me a means of getting the probabilities in this situation or in any other situation where you have the same application, that what kind of application, that you have insufficient information and the system could be in any, I mean, whenever you have that ensemble, you get that ensemble, which will generate a density operator. So a reverse way, given the density operator, diagonalizing the corresponding matrix will give me the ensemble. Now what is the ensemble? All the eigenstates and the corresponding probabilities. This will give me the ensemble. Okay.
Mod of
So,
alpha 1 square alpha 2 square.
yeah.
This will be mod of alpha 1 square.
Yeah. Those will be the probabilities numbers. They will add up to 1. So the density operator must have the trace of rho equal to 1. Trace of rho is just this diagonal elements. So when I get all this, what I now do is the following, that okay, so now I am interested in a mixed state for which all probabilities are equal.
Equiprobable.
Yeah, all diagonal elements are equal. So your diagonalized matrix is some alpha into I, where alpha is, alpha, all probabilities are alpha, 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 alpha. All the diagonal elements are the same. This is called random mixture. So when I have my rho to be an identity operator proportional to, is proportional to the identity operator, the proportionality constant is some common probability. All the options, all the have an ensemble where there are eigenstates, and each eigenstate has the same probability. That will generate the corresponding row with the same probability. When you diagonalize, all the probabilities will be the same number will come here. I can take it out. It will become a identity matrix or identity operator, and so you will get this. So this is the random mixture. Now the very interesting property of this random mixture is the following. So suppose I write like this. So this is the random mixture. So I can write 1/2 0 plus 1/2 1. This is the example of random mixture. I am very sorry. 1/2 0 0 plus 1/2 1 1. This is an example of a random mixture. Now the beautiful thing about a very interesting thing about this is, when I construct a random mixture using a particular basis. Now I am using this basis to construct the random mixture. That is, I am using some Pauli operator or something like that. It's eigenstates and random mixture. So once the random mixture is created, now this is 1/2 into bracket 0 0 plus 1 1. What can you say about this? Projector 0 0, projector 1 1. What can you say about this? You? Ket 0 and Ket 1 forms a orthonormal basis. So I am summing over the projectors of all elements in the orthonormal basis.
It's a random mixture.
No, what do you get? If I take an orthonormal basis, take the projector of each state in the orthonormal basis and sum it, what do I get? Identity. This is resolution of identity. Resolution of identity. We have seen it. So this is identity. So I have got identity here. So the beautiful thing about it is, suppose I have another operator, and suppose this is its basis. Then the same state, same random mixture state, can be expressed as 1/2 alpha alpha plus beta beta. Yeah, some other orthonormal basis corresponding to the eigenstates of some other operator, some other observable. This the same random. So for example, what say unpolarized light. If you get unpolarized light, it's a random mixture of all possible polarizations. You can I mean, there is nothing special about a particular polarization. You can express it as a some kind of random mixture of some linear polarization, circular polarizations, or whatever. It doesn't matter. Okay. So this is an example of a random mixture.
So we can represent it either HV or
Yeah,
any two orthonormal.
HV or some circular RL,
Diagonal or circular.
anything. It doesn't matter. So this is I mean, this light which comes out of a simple, which is unpolarized, it is a random mixture of all polarizations. So this is, I mean, could be any kind of orthonormal polarization you get. That is, yeah, you can think of anything. It doesn't matter. So this is what the beauty of it is. So this random mixture has a particular property that it is some kind of something like this stands out as an independent of which operator you are measuring. You can measure any operator, take its eigenbasis and construct a random mixture with equal probabilities. You will get the same random mixture. You cannot. There are no different random mixtures. There is no way of constructing different. It's a unique random mixture is unique. Okay. So I can now use this random mixture to define my unit of quantum information. Now what do I do? See, yeah, okay. So how do I do it? So so suppose I have a qubit. Now let me lock onto qubit. So that is necessary. So now, yeah. So now in general, I mean, I just forgot to say it. So in general, whatever, suppose you have some alpha psi 1 plus beta and mod alpha square psi 1 plus mod beta square psi 2 okay. Then the amount of ignorance, I mean how much ignorant I am about this, whether it is psi 1 or psi 2, is expressed by what is called 1M entropy. It's given by E minus summation of I lambda I log to the base 2 lambda I, where lambda I mean this alpha beta, for example, this I call them lambda 1 mod square and lambda 2 mod square. So I running from 1 to 2. So this is the entropy. This is the amount of ignorance I have about this state, which state the particle is when it is in this particular density operator. Okay. So now suppose I start with my random mixture and measure on it any operator, it doesn't matter. It is independent of measurement. I am going to get one half. I mean I am talking about only two options. I mean the dimension is 2, that is okay. So then I am going to get one half. So this entropy will be minus 1/2 log 2 lambda 1. I mean 1/2 minus 1/2 log 2 1/2. The same thing as we got in classically, but in the quantum mechanical setting. So that is equal to 1. And I can now use this as a gain in information. Okay. So I have to start with a random mixture and make a measurement to get the state. It will be one of the eigenstates, obviously. Doesn't matter. Okay. So whichever eigenstate, if I get some eigenstate, how much information have I gained It is 1 unit.
Can we think that any material which you are going to use as a quantum experiment initially is in state?
No, I don't know
mixed state,
initially.
no? In the mixed state. Initially it is in the mixed state.
Not only mixed state, in order to define this unit of information, I assume that it is in the random mixture.
No, for
No.
this particular case.
For-
Otherwise it can
Otherwise, it could be, yeah. If I measure and I do not record the result, the whatever state I get
this will give the information.
it will be a mixed state, yeah. And you can define the corresponding density operator like this and so on, no problem. Of course, this is not the only way mixed states occur. Mixed states will occur whenever you don't have sufficient information to pinpoint in which pure state the system is. Any such situation, you will get the mixed state. Okay? But in order to define this unit of information in this quantum case, I define it in the following way, that I start with a random mixture and then I make a measurement, and if I do that, how much information do I get? That is 1 unit. And this is I have obtained this. This is the information. This is this is equal to 1. That is clear, because this is just the calculation of von Neumann entropy
For two cases.
for the two cases. For you define it for a qubit, and you call it just as you call the corresponding classical analog as bit, 1 bit of information. This is 1 qubit of information. So this is what this is all about information that I wanted to tell you. And we'll go to now quantum algorithm. We'll take one quantum algorithm and analyze it now. So there is one little thing that I have, because all the other of my colleagues talking about quantum mechanics, they were basically talking about quantum mechanics, not essentially connected with quantum computation, but as a background which is required. So they all formulated in terms of wave functions, while here it is we use only bra and ket notation. Okay, we systematically defined all bra with respect to ket and everything, scalar products and everything. So what is the connection? Connection is this. Suppose I have now I start with a position operator, position of a particle. Okay, so that is the physical quantity corresponding operator x hat. So the particle, suppose I confine to 1 dimension, so particle could be anywhere on that line, and it's a continuous thing. So every possible position, every possible point on that line is a possible eigenvalue. Okay, so that is a continuous eigenvalue. So so when in the case of discrete eigenvalues, we did this. Provided this alpha is a, is a orthonormal basis. For orthonormality is essential for the basis. If it is orthonormal, I can always write it like this. But now this is a continuous thing. So I will parameterize the line or parameterize all the eigenvalues by some variable x. So I have to replace this sum by the integral, and this will give me x into bracket x psi dx. Just the analog of this, but since it is continuous, I have to integrate. That's all. Now look here, this basis, suppose I change it to some other state phi, then I will get again x basis x phi. So information or the contents of this state are completely given by the coefficients, this scalar product. Okay? So you will use the same basis. Basis is not going to change. What is going to change is the scalar product multiplying into the basis. So this is completely, this contains all the information, everything that you have to know about this state psi. And since x is a continuous parameter or continuous variable, this is, this one, I can write it as a function of x. This is a function of x, as this is a complex number, as a very x, this I continuously go through the complex numbers. That means this object, this scalar product continuously varies with x. So I can view it as a function of x. Similarly, here it is, I have a function of x here, phi x. Okay. And what is the probability? Probability is, why dx? Because you cannot think of, you cannot assign probability to a point in a continuous way. You have to think, you have to ask for the probability of the position lying between x and x plus dx. So this is the probability. So that means this just means that this is the probability. Because this is just a function of. So this connects. You can, it is equivalent. You can either work with wave functions or you can work with Kates and Bras. Kates and Bras are more general and they are more transparent, more obvious. They emphasize the difference between basic structure and its application to particular cases. It becomes quite apparent if you use Kates and Bras. It's not very apparent when you use these wave functions. Okay, so you can now you can go transform from, suppose you change this x to p. Again, it has a continuous spectrum of eigenvalues. Okay, and you can do the same thing. So you will get a state. The state is the same, but you will get its representation in terms of functions of p, that is momentum. Okay, this will be the Kate psi is the same state, but then what I will do is, now this x is replaced by p and this x is replaced by p. So you will get this is a function of p, psi or whatever, psi prime, psi bar p if you want. No problem. Same, I am not changing the state, I am just changing the representation. You can actually mathematically transform from one variable to the other variable. Psi of x, if you know, you can find out psi of p or psi bar of p, whatever you are talking about. Okay. It is the same state, that you have to understand clearly. I am not changing the state at all. That's it. Now let us go to take some algorithm, because I promised you that we did this Deutsch algorithm, so let's generalize it. So let me, okay. Okay. So what I do now, Deutsch algorithm takes a function which maps a one bit to other bit. Okay, so the argument of the function contains only one bit. Now, if the argument of the function contains two or more bits, so it will be 2 or 3, 2 again. So the value of the function is only one bit, it is either 0 or 1, but it maps a string of not 1 bit to 1 bit, but say 2 bits to 1 bit, 3 bits to 1 bit, 4 bits to 1 bit, and so on. So if you look at how many functions, suppose it is 2, then the total number of such functions is 2 raised to 2 raised to 2, that is 16. So you will get, you can actually work out these 16 functions. But the point here is that not every function can be classified as either balanced or constant. You can have functions which are neither balanced nor constant. So let me pick out a subset of these functions which are either balanced or constant. So just take out a subset of this, and this algorithm, which is Deutsch-Josa, D-U-T-S-H, Jo. Yeah, this person's spelling always beats me, whether it is ZS or SZ. I don't, but this is Deutsch-Josa algorithm. Okay, so, okay. So just for your this thing, what you are doing is you are considering the maps of the functions which map xn minus 1, xn minus 2 to x0, x1, x0 maps to 0 or 1. And you select only those functions out of these functions which there will be 2 raised to 2 raised to n such functions. Out of that you select that subset which can either be classified as constants or balanced, and then apply this algorithm. So what is the algorithm? To find out, I have not stated the problem here. So the problem, I mean, there is nothing great about stating the problem. So the problem is, to given a function you have to find out whether it is balanced or constant. That is the algorithm. So generalization of Deutsch algorithm. So for that you have to use this notation that I have already introduced. So H with this star n, not star, but I mean tensor n is just H, tensor H, tensor H, tensor H n times. This is the first thing that I have to introduce. Second, that we have already seen that H tensor n on 0 is summation over k or I, whatever that is. How do I do that? Yeah, that's summation over, okay, I use S here, summation of S, sorry, it is 1 upon square root of 2 raised to n summation over S running from 0 to n minus 1, or 2 raised to n, I mean 2 raised to n minus 1, and that is just x. That x runs from 0, 1, 2, 3, etc. So if x equal to 0 means there are n zeros, x equal to 1 means there are n minus 1 zeros, and last digit is 1, and so on. I mean, you take the corresponding binaries, that will give you the corresponding state. So for example, 3 zeros, the state like this just means 0 tensor 0 tensor 0. This is the correct description, but I never write like this. I'll always write like this. And not only that, this I will write at just 0. Huh?
Here we cannot write n tensor n 0 to the power tensor n. Then can't we write like that? As we have
No, this is the operator. The H is the operator, and then I am writing like this. Okay. So H is the H gate. H stands for H gate, and I am applying H gate.
At H we can say there are n.
No, H tensor H to this means I am applying H to the first qubit, second H to the second qubit, third H to the third qubit, like this. Okay.
So if you write 1, it corresponds to the binary, if you write HN 1, it means 0, 0, 0, 1.
1, something like, yeah.
Binary.
Yes, yes. You have to take the binary and then apply H to every qubit, obviously. It's a short notation, so I can do like this. So fine. So all this I have said, but I mean I keep on saying the same thing again. Okay, that's fine. So now what I need is this. Suppose, I mean what I need is operating h n times on some x which is not 0, some x greater than 0. Okay. So that is some other eigenstate like 1, 2, 3, 4 or something like that. That turns out to be 1 upon square root of 2 raised to n, okay, summation s running from 0 to 2 raised to n minus 1 minus 1 raised to x circle s. I will define it, x circle s is this is s running from 0, so this should be s. Now this I am running variable, I am taking s, so it should label the same. So that means s0, s1, s2 like this. So I have to define this. Oh, let me, this is confusing. So let me erase this. Okay, so this is what, now what is this s? X circle s means, that is, sorry, xn minus 1, xn minus 2 up to x0 circle sn minus 1, sn minus 2, s0 is given by, this is given by xn minus 1, sn minus 1 XOR or xn minus 2 sn minus 2 XOR dot XOR x0 s0. The bitwise, that is, I mean xn minus 1 is one bit, either 0 or 1, sn minus 1 is another bit, 0 or 1. Multiply these two bits, take whatever product is there, write it here, XOR again the corresponding two bits, multiply, put it here and put this XOR. So you will get finally one bit out of it. When you XOR, keep on XORing this, you get one bit out of it. So this is the column vector नाही, डायरेक्ट प्रॉडक्ट घ्यायचा, म्हणजे हे समजा 1 असेल आणि हा 1 असेल तर 1 into 1 1, हा 0 असेल तर 0 into 1 0.
आपण हॉरिझॉन्टल टाकलं आणि एस ला व्हर्टिकल टाकलं आणि त्याचं मल्टिप्लिकेशन केलं तर त्या पर्टिक्युलर एक त्याची व्हॅल्यू घ्यायची आणि एक्सॉर करत जायचं.
हां, दॅट इज, तसंही करता येईल तुम्हाला, तसं नाही, एक रो वेक्टर घ्यायचा, एक कॉलम वेक्टर घ्यायचा, put it like a scalar product, and the point is you are doing XORing, that is something new, that is otherwise you just add them as they are.
XORing perhaps is giving parity, right? Number of odd, whether they match or don't match, either odd times or even times.
Probably, possibly, but let me think about it. So I mean, as far as this algorithm is concerned, it's not nothing like parity or something like that. This is you find that if you apply h gate to this, I mean,
Actually, whenever it is 0, it will be half 1 by root to 0 1, and whenever it is 1, it will be 1 by root to 0 minus 2. So that it is actually capturing.
yeah, that is minus 1 raised to that will give you that corresponding 1, or if it is 0 it will become 1, if it is 1 it will become minus 1. That's right, that is right, that is precisely what is happening.
Yeah, I meant the application of XOR for so many number of times, essentially making sure that the parity is ordered.
Okay, fine, I agree, yes.
So and that is what we are using as the power of that minus 1. That odd or even parity.
odd or even parity you are using, but that is the point is that, I mean, if you actually work it out for say n equal to 2 or n equal to 3, this minus 1 raised to x circle s will exactly correctly give you the plus and minus signs of this superposition. So parity is required for some other applications. I mean, but that's
There
what I'm
will
saying,
not
that,
be parity per se.
yeah, this you can view it as parity. That's no problem. But the purpose here is to correctly obtain the superposition. That's what. So that is the thing. So yeah. So this is the thing. So now, okay, let me draw the circuit. Where is the circuit? Okay, this is the circuit. Circuit is this. Measurement. Now the target thing is 1. This is left out. You don't do anything. So let us work it out. So from your circuit, what is the input state to UF? Input state to UF is just look at it, you must understand it. So this is what? K0 tensor n means what? Means this. And H is tensor n on this means this. This whole picture I don't want to draw. I mean, so I just say 0 tensor n, and this is this. When I make a scratch, that means this. This is a notation. So this is what the thing is. So that means my input is H tensor n on 0 tensor n, tensor H on 1, Ket 1. So that will be 1x. So this is not n times. Target register consists only one qubit, and that is Ket. So this is what it is. So this is the thing. Okay. Okay, so this is fine. This is fine. So when I act by UF, we have already done this. What will happen to it? So UF on the input state, say x, 1x, is given by, action of UF on this is given by minus 1 raised to fx Ket x. So I can write like this, 1x So this we have done yesterday. I mean, when we did the phase kickback and its applications to this. When we did it, you get this phase which is controlled by the value of fx. So the action of UF on the total input state will be UF on 1 upon square root of 2 raised to n summation s running from 0 to 2 raised to n minus 1 s. That is equal to, now UF is a linear operator, so it will act on every term in the sum, so that will be equal to 1 upon square root of 2 raised to n summation s running from 0 to 2 raised to n minus 1 UF on s into 1x. So this is equal to one upon square root of 2 raised to n summation s running from 0 to 2 raised to n minus 1 raised to fx fs S okay. You should take it down and then ponder over it later, okay? Go through it, because just now you may not understand it, but that's very simple. It doesn't, there is no catch in it, there is nothing like that. So it's okay. So this is the action. So what we have done up to here, we are now here. We have the input state and we have acted by UF on the input state. So in the circuit we have produced the output of this UF, and that is this, okay. Now what is it? What is the next thing? We have to act by H tensor n on this, on the data register, on the data register part of it, okay. That is that sum, okay. So when you do that, let us see. Okay, so I have so I am just taking out this data register part and acting on this. So that is equal to again, this is a linear operator, so it will act on each term. So that will be 1 upon square root 2 raised to n s from 0 to 2 raised to n minus 1 raised to fs h tensor n on s. So that is equal to 1 upon square root of 2 raised to n s from 0 to 2 raised to n minus 1 minus 1 raised to fs into bracket 1 upon square root of 2 raised to n summation s running from 0 to 2 raised to n minus 1 minus 1 raised to fs. I mean sorry, minus 1 raised to s circle z okay. So this way I have already derived that action of h tensor n on some x not equal to 0, that gives you that product minus 1 raised to that. So this is the thing. So this I can write as 1 upon 2 raised to n, because I have square root of 2 raised to n here and square root of 2 raised to n here. So 1 upon 2 raised to n into bracket summation z running from 0 to 2 raised to n minus 1. What is happening here? It should be z here. It must be z here. Correct it. So z running from 0 to 2 raised to n minus 1 into bracket summation s running from 0 to 2 raised to n minus 1 minus 1 raised to fs minus 1 raised to s circle z is complete and z. So this part I will call g of z. This part I will call g of z, because s is getting summed over. So this final sum will not depend on s. S is getting summed over, so it will only depend on z. So this is a function of z. So I have this. This is then 1 upon 2 raised to n, a compact form, z equal to 0 to 2 raised to n minus 1 g z. So now let me compute the amplitude for z equal to 0. So what will be that? g0 upon 2 raised to n. So when this is 0, this will be just 0 circle 0. So that will be, I mean, s circle 0. So s circle 0 will be 0. I mean, okay. I mean, it will be, say, s is first, say, s n minus 1 into 0 XOR s n minus 1, s n minus 2 into 0 XOR, like this. So this will be 0 XOR 0 XOR 0 XOR, this is 0. S circle 0 is 0, z equal to 0. I am just singling out one term, z equal to 0. So amplitude for that. So that is g0 I want to evaluate. This is 1, and fs is, so fs is either 0 or 1. So let me call it 0 or 1. So I will call it h. So this is minus 1 raised to h. So that will be, this is equal to 1 upon 2 raised to n summation s running from 0 to 2 raised to n minus 1 minus 1 raised to h and minus 1 raised to s the circle 0 is 0, so that is just 1. So that is equal to minus 1 raised, I mean, so it will be either all minus 1 or all 0. So if h means that is the fs. So Fs, if it is 0, then it will be okay. So let me just see it. So this is okay. So this is the thing. So z equal to 0, you will get this is 0 minus 1 raised to Fs. So Fs is I mean, so if yeah, this I forgot to write. If f is constant in this, if f is constant, then it is either, then for every term Fs is either 0 or 1, call it h. See, f is constant, so that means it is the same value for all s. It is either 0 or 1. Okay. So this is minus 1 raised to h. This is minus 1 raised to 0, so this is 1. And so it is, I suppose h equal to 0, then it will be 1 plus 1 plus 1 or 2 raised to n times, from 0 to, I mean 2 raised to n times. So this will be 2 raised to n, and this is if it is 1, then it is minus 1 minus 1 minus 1, so it is minus 2 raised to n. So this will be 1 upon 2 raised to n is there, then 2 raised to n times plus or minus 1, that is equal to plus or minus 1. So the amplitude for z equal to 0 is plus or minus 1. What can you conclude about it from this? What is your conclusion after about this? This full superposition is there, z equal to 0, z equal to 1, z equal to 2, all these terms are there. The coefficient of z equal to 0, ket z equal to 0 is 1, plus 1 or minus 1, doesn't matter. So what is the conclusion? What is your conclusion? What can you say about the coefficients of all other terms? 0. It has to be 0 because it is normalized. So the first coefficient mod square plus second coefficient mod square plus third will all add up to 1. Now first coefficient is already plus 1 or minus 1, its mod square is 1. So others must be 0. So when f is constant, the probability of getting, if I make a measurement now, the probability of getting the result ket 0 is 1, and you won't get any other 0. Now if f is balanced, then okay, then you have g0. Now again this is a bit boring, but you have to go through it. I mean, it's not, life is not always fun. Okay. So this is what you get here. Okay. So again, minus 1 raised to s circle z is again 1, minus 1 raised to 0, that is 1. So minus 1 raised to fs it will come. But now fs is half of the times fs is equal to 0, and half of the times fs is 1. That is the balance. No? Balance means half of the times it is 0 and half of the times it is 1. The value of fs are equal, both zeros, number of zeros and number of ones in that value column are equal. Okay. That means when fs is 0, this will be plus 1, and if fs is 1, it will be minus 1. But since zeros and ones are equal, this plus 1s will be equal to minus 1s, and this will be 0. So the probability of getting ket 0 for a balanced function is 0. So what is your conclusion? Conclusion is you make a measurement. If you get ket 0 out of it, the function is constant. Constant. If you don't get anything ket 0, you get something else than ket 0, then the function is balanced. So now let us, I mean, just how much time I have? What is the time? 110. About time hai. Okay, so now
So I think, sir, maybe we can go on till 1:15.
115. Who is saying this? Huh?
They will close the canteen. They have
The
fixed
canteen will shut down.
Okay, give me 5 minutes, let me see. I mean, just 5 to 7 minutes. I mean, two interesting things that I want to just see. So, DJ algorithm, this Deutsch-Zosa is a deterministic algorithm. So, it will definitely tell you after the final measurement, it will definitely tell you whether the function is constant or function is balanced. But now, suppose you want to do it classically, then how do I do it? Then I have to measure, or I have to find out the value of that function at all its arguments. So, how do I conclude whether it is constant or balanced? See, the first time I get another value as a function, suppose first value is 0 and second value I get 1, then it has to be balanced. Because it is already, we have seen that we are only collecting those functions which are either constant or balanced. So, it must be balanced. Now, in order to get the constant, suppose I keep on getting 0, 0, 0, 0, 0, it's not changing at all. So, how far do I go? No, till the mid. Because if it was balanced, the number of ones and number of zeros are equal. So, if I get a 0 after the half of it, that means it is constant. 0 or 1, whatever, that the same thing. So, only that. So, I have to check, maximum check I have to do is 2 raised to n minus 1 times. I have to keep,
Plus 1.
plus 1, okay. So, this is what I have to do, those many checks. So now this circuit or this quantum algorithm is extremely powerful. Why? Because I am applying UF only once. It's a constant, it's extremely powerful, extremely efficient. And while here it is exponential, 2 raised to n. So, if you do it deterministically, then it is it's far more efficient. But now other way is, suppose I make room for some small probability that my result of balance or constant can go wrong. Make room for such a probability, small thing. Then what will happen? Yeah, then I was planning to have one more algorithm, but I mean now it's not possible. Okay, so some probability, I mean some that the things can go wrong. That is, the function may be actually balanced, but I declare it to be constant. The function may be constant, but I declare it to be balanced. That may happen, but the probability of that is a very small probability. Okay. So what I will do is, I will arbitrarily take some m values and evaluate the function f at these m values. And on the basis of these m values, I just find out whether it is constant or balanced. So, what is the event in which I can go wrong? That is, the event is getting some output m times, getting the same output m times. Getting the same output m times, and what, and f is balanced. See, out of these m outputs, if two of them differ, then I know it is balanced. There is no problem. The problem comes when it is constant. So out of this m, I am getting all the results, all the values of f to be the same, and still I may fail. So what is the probability that in this case I will fail? The fail is the probability that I get the same output m times and f is balanced. This is the, so what is the probability? The first probability is PA. I leave it for you to see this, because why 2? Okay, let me explain. See, 0 or 1, so each time the probability is a 1/2, whether getting 0, whatever value. Okay, so m times I am getting the same, so I will get 1/2 raised to m. But there are two possibilities. I might get the same 0, I mean same which is 0. I am getting the same result which is 1. So you have to multiply by 2. So this is the probability. Okay, and PB. This is A. This is A. Event A. This is event B. So PB is what? PB is just 1/2, because there are only two options. The function could be either constant or balanced. So to declare, maybe wrongly or rightly, whatever, to declare it to be balanced, to be balanced is probability is 1/2. So probability of the total thing is PA into PB, that is equal to 1/2 raised to m. So if I choose my m, the number of times I have evaluate f, to be less than epsilon, so I want this probability, failing probability to be some small number, I fix that epsilon, and I choose my m such that 1/2 raised to m is less than epsilon. Then with whatever small probability I want, I will get the correct result. I will fail very sparingly. That's right. Okay. So that means the classical algorithm, classical probabilistic algorithm, is competing with the see, because for example, if m is 53, then 1/2 raised to say 53 is 10 raised to minus 11, something like that. So epsilon I can choose to be 10 raised to minus 15. So I will get the probability of failure is less than 10 raised to minus 15. So that is, I mean, don't have to worry about it. Okay. So okay. So time taken by this algorithm is the m evaluations. So time this m evaluations is independent of m, of n. The what is the number of string of bits which is getting mapped. Okay, so you have what I mean, that the unit of time for one evaluation will change, but the total time is just m times that time. So it's a constant actually.
M is in our control.
Huh?
We have to choose.
M I choose is that 1/2 raised to m is less than epsilon. I first fix my epsilon. I want the failure probability to be some small.
And that is the reason why it is independent of m, because you fix your epsilon.
Yeah, I fix the epsilon. So I mean, the main point is how to evaluate an algorithm. It's evaluating the algorithm means the size of the input and the total time taken must be, if it is exponential with the size of the input, then this algorithm is bad. If the size of the input is linear or polynomial, then it's okay. But here it is independent of the size of the input. N could be anything. I am just evaluating it. There's a constant. Some constant time is involved. That's all. Nothing else. For any given n. So that is independent of your size of the input at all. Okay. So that means it is at par with my quantum algorithm. So that's not a very nice news. but there is another algorithm which we are not doing. Don't worry about it. I planned to do that, but that's okay. It's called Bernstein-Vazirani algorithm, where you use the same circuit, but you fix your f, some f, so some constant a into s. So let me check that. A into x. So f of x is equal to a circle is x. This is the function. So fix this function and then go through this, then you will get and then find out. Here we found out the probability of getting ket 0. You find out the probability of getting ket a, and that will turn out to be 1. So this unknown constant, you give me this a, you know this a, you give me this, and I go through the circuit and find out a.
Which algorithm?
Huh?
Algorithm.
Bernstein-Vazirani. Bernstein-Vazirani. Okay, so you can try it for yourself actually. Same algorithm, same circuit. F particular f. Work out and you will see that you can find out. And while evaluating the complexity, you don't have to. Here, if you want to find out the complexity for this Josa, Deutsch Josa, you have to include the time of measurement, making last measurement that we do, because unless you measure, you will not know whether it is balanced or constant. After measurement, when you get 0, then you conclude that it is balanced. I mean, it is constant. If you don't get ket 0, you conclude that it is balanced. So measurement is necessary. But here measurement is not necessary. I mean, I generate this, I generate A. I don't have to. I mean, algorithm doesn't tell me that I have to measure it to complete the algorithm. I can use that A for further computation. There is no problem.
Measurement time is
Measurement time is excluded for Bernstein-Vazirani. So it is a quite efficient algorithm. And you can see that there is no probabilistic classical algorithm competing with it, because even if m is, you take m to be say n minus 1, I mean total times 2 raised to n minus 1, the last measurement is probabilistic. So you cannot, you can have whatever result, it doesn't make any difference. So you cannot have a probabilistic algorithm for Bernstein-Vazirani. So Bernstein-Vazirani beats classical algorithms complete, totally, no problem. They use UF only once, that's it. This circuit uses UF only once, so your function evaluation is only one. Is that okay?
yes.
Okay, thank you very much. I think this is the last lecture, my last lecture. So I want to thank you, thank all of you. I hope I was able to give you something. But that's for you to decide. But it's only hope that I have done something. Okay, so fine. Thank you so much.